Okay, test. Again, gonna wait a second for Twitch to catch up. Twitch seems to be catching up. Any second now. Any second now. I'm basically waiting until I see the message that until the stream elements thing catches up. That's usually a sign that Twitch is caught up. I'm not seeing it this time. I'm gonna assume that this is live again and continue from there. Sorry about that. Yeah, my graphics card seems to have crashed and brought down the stream with it. So yes, what I was saying before this, the reason I haven't been trying to compile to check all of this is simply that I'm in the middle of a big refactor, and there we go. Here comes stream elements. I'm in the middle of a big refactor, and I am porting all of the old code to a completely new version of it. And until I'm done with the basics, the project is not in a state where it's going to compile. I did not try to do this incrementally. I just broke the entire project. But we're getting close to a point where we can actually compile, and the sooner the better, because we're going to have a lot of errors to go through when we actually can compile. So, we had just finished taking care of struct expressions in the context of functions. Oh, there was a third validation functions, wasn't there? And there's range expression, but we don't care about that yet. And I think we were about to tackle function calls. So function calls, I'm gonna go look at what the old code pre-refactor looked like to try to see how much we can salvage from the old code. But I can probably start thinking about what it's going to look like, because it's going to be a function that given some monad, oops, I typed that wrong, given some monad m in which we're going to operate, we'll put more constraints on that later. And given that's going to be probably a path info resolved, as in that's the name we found of like a path to something, like B in the module A or F or whatever, and we need to figure out what that thing is and is it a function. Refresh. Was that message from me? Is something broken? Okay. Let me actually also refresh my Twitch just in case I've missed some chat messages. But yeah, sorry about that. Yeah, my graphic cards decided to take down the stream by crashing. It happens sometimes. Rarely though, thankfully. But yeah, we are going to have a function call, so we are going to have the name of the thing in the function call that we have already resolved, so at this point we know what thing we've tried to call, and we're going to have a bunch of arguments which are the values for the fields. And those are going to be, as a result, a bunch of with location expression resolved, which I'm going to replace by a resolved expression. I'm going to make use of type aliases in the corresponding modules as part of this refactor. Okay, so that's what we're going to have. And we're going to have to decide, is this valid? And if it is, we are going to emit a new typed expression that matches this particular function call. So this is theoretically the function name, and those are the function arguments. Let's go have a look at how this was implemented pre-refactor, where we were doing both the name resolving and the type checking and the validation at the same time. Was it in this one? Analyze function expression, yes. Call expression, there we go. This would be this. Resolved function call value, this is what we're going to start with, as in this thing, the path we have here, is it pointing to a function? Now half the work has already been done, it's going to be easier. Then trying to resolve the arguments, that's fine. Check the number of argument matches, that's also simple. Here is where we are going to do the same thing we do for structs, where we are going to try to do type inference to figure out the type parameters of the function, if it's a generic function, based on the arguments. If we can't figure them all out, then we're going to have to emit an error. This is going to be very similar to what we do for the struct code, but since the structure is a bit different, I'm not sure how much we're going to be able to reuse the code. We might have to duplicate it. The true path thing is about function instantiation. Everything there has changed. Okay, so here some of the code can be reused, some of it cannot. One thing I have in mind is, did we do, because we also changed the way function instantiation work as part of this refactor. I think function call is where we are going to need to do, we have instantiated a generic function, therefore it needs to be included in the symbols of this compilation unit. Therefore, we need to register it for compilation, which is not something we're doing as part of this. So I'm going to copy the old code just for reference, even though the new code will be completely different, and we can write the new version. Oh, for the application order, you meant for the compose? Because if it's the compose, I'm happy to show you a small example in GHCI. Yeah, let me do that then. Let's open a GHCI that you can see. There we go. Is it functor compose? It is not functor compose. Where is it again? It's data functor compose. Okay. And let's do a traverse2 function that is traverse.traverse. So if we look at the type of this traverse2 that we've just created, that is a traverse of a traverse, it looks like this. I have a function from A to some B in some functor f, whatever f ends up being. I have a, I've done traverse. I have something that can be traversed. That's a bunch of things that may or may not contains value of type A. And this basically applies this function on the A values and lets the actual type, if it's traversable, it will know how to do that, do the mechanics so that the F thing, oops, sorry about that, I pasted some stuff by mistake. Okay, let's redo traverse again. That the functor around the B values gets brought back up above the values of the traversal. So if I use this, but in the case of list, for instance, when the thing that is traversable is a list, then there is a function from A to some kind of B in a context, takes a list of A, returns that list of B values that correspond to the application of that function on the A values, and the context has been brought back up. And for instance, the context can be something like maybe. So that would be, given a function that to the A gives us a maybe B, takes a list of A, returns a maybe list of B that will contain a list of B if all of those return just. So if we do a traverse of, I have no idea, x, if odd x, then just x, else nothing, on a list 1, 3, 5, since all three of them are odd, we get just 1, just 3, just 5, and traverse brings back the monadic context back to the top, basically. And we have just 1, 3, 5. If we had an A even value in this, it would return nothing. The whole thing would return nothing. The thing is, we can nest traverse. I showed the example of like traverse to, well, now I have here. Traverse 2 is traverse dot traverse. Traverse 3 is traverse dot traverse dot traverse. And the type of traverse 3 is going to be, I have the same applicative f, I have traversable types t1, t2, t3. I still have a function from a to some kind of b in the functor f, basically. But now we have a t1 of t2 of t3 of a, and this gives us an f of t1 of t2 of t3 of b. So traverse is responsible for like, okay, now that we have applied the function deeply nested into the thing, how do we bring this context with us back to the top? And like this nested traverse, I could use the same example that I had here, this traverse 3 thing. If instead of having lists of numbers, if I have lists of tuple of string, I'm going to use only one value, list of tuple of string and maybe value. So this is a list of tuple of maybe thing. So we are nesting 3 times, but this gives us still a just one because it has applied the function all the way deeply nested in the thing and brought the thing all the way back to the top. Maybe not, let's not use a just here, let's use a right here, just that way it's clear which one is which. So it applies the function all the way inside the thing, but traverse, the whole point of the traversable class is how do we bring the thing back to the top? Where it becomes a problem is, let's imagine that my function here that I'm using for the traverse, instead of being something that just gives me a value, let's say it gives me, what would be an interesting example? What would be an interesting example? Let's say it gives me an IO maybe value. So let's say that it's pure just X, an IO maybe int, basically. Now, if I do that, that's perfectly fine. That should still work. And I do get, indeed, this is in IO, because IO is the thing here, the F has been brought back to the top, but the maybe is still nested all the way back in, because in this function here, which maps to this A to FB here, the F is IO, brought back to the top. The B is maybe int, that stays inside. But what if I want the maybe to be brought back to the top as well? Well, I could redo a complicated traversal. Of like, okay, well, I redo a traverse to bring back the maybe one step, then I redo a traverse to bring back the maybe one step. I could redo that thing myself, basically. Probably by using a bunch of sequence, where sequence, or even sequence A for that matter, given some traversable thing that contains value in a functor, brings the functor back to the top. So if I have list of maybe value, gives me a maybe list of value, which brings back the thing. So I could use that, but another approach would be to use compose. And compose, that thing is a bit hard to read, but given a f of g of a, where f and g are functors, it returns a compose fga, which is only one value around a, that composes f and g. So if I have to take a somewhat similar example, if I have a list, a tuple of string and just int, and I compose them, the type of this will be a thing that composes tuple of string and maybe for value a that happens in this case to just be an int. So if I go back to this example where I'm using this traverse deeply nested to apply something on the one here, which is within a list of tuple of either values, and I apply my callback function on this int, and it returns an IO maybe thing. If instead here I do a compose of pure and just x, the type of this will be a compose IO maybe of int, and therefore the f thing in my traverse, where's traverse? Is it still in the screen? It's still on the screen. This f here will be the compose that contains both functors. So the thing that traverse will bring back all the way to the top will be a compose IO maybe, so the maybe will be brought back with it. It's not able to show an IO maybe thing, but if I look at the type, the result of this is a compose IO maybe of this list of tuple string either a int. So the maybe has come back all the way by becoming one with the functor, becoming, instead of just IO that contains a maybe, it's now a functor made of IO of a maybe composed together thanks to compose. And if I then do a get compose out of this, I'll get an IO maybe thing. I've brought back the maybe with me by composing it with the IO. What I use it for here in those functions here, if I go to here for those things, I'm using a traverse on a bunch of values. And this try nested is an alias I've introduced. Well, I haven't actually implemented it yet, but it's going to be there. It's basically this try will give me a maybe value in my monad, but then I do a compose. So it becomes one thing, maybe, and my monad. Traverse brings it back to the top, and this thing does a get compose and then handling the maybe. So I don't have to do all the sequencing myself. Here for this, for one layer, doing the sequencing would not be too complicated. But the reason I've introduced those things is I often have like 2, 3, 4 layers of nesting, and then having to do all the sequencing of the maybes myself would be very complicated. So that's the logic there. And I think it's the first time I really make use of compose. I usually don't have much of a reason to do that. Here, the main reason I have all of those maybes that stay here is like, I'm trying to do error recovery. So there are a lot of error mods will have, of course, I'm always happy to answer questions. A lot of like time you will just have like an either somewhere in your stack of monads, and you can just say like, well, throw and just short circuit, and we will make use of short circuiting quite a lot, because often you can't, please do ask questions. I'm always happy to help. But here I want to try to do error recovery, so all of those have a try, so I can still try the next field and then compose the result into a maybe at the end. That will be just only if all the fields have succeeded. But yeah, please, again, I always welcome questions. In the meantime, I'll start thinking about... I mean, I already have one, right? I already, it's not exactly explaining monads for beginners, but one of the only videos on my channel, and I want to make more, is one where I talk about monads. Specifically, I talk about the problem about monads, and that is a topic that is very dear to me. Earlier this year, and it's something I want to reopen, but I haven't had the time yet, I even ran a thing for a few weeks where there was a site you could book like 15 minutes of my time, and I would explain to you that why everything you think about monads is wrong, and you already know about them, basically. Thank you for the link. And yeah, basically, I ran this course a few times of like, I'll take 20 minutes of your time, and I will explain to you what you need to know about monads and why your assumptions about them are wrong. Okay, I'm gonna, full disclosure, there's a reason as part of this refactor I haven't done yet the diagnosis monad, because it's gonna prove to be a very good example for the thing I'm about to rant about. So for people who view this on YouTube in the future, someone just redeemed the rant about monads extremely expensive perk on this channel. Let's abandon function calls and let's open, where would that be? Internal diagnosis, I suppose? And let's create a diagnosis monad. But first, I am going to fucking rant about those things. So, the problem with monads is not monads themselves. Monads themselves are just absolutely, completely fine. But the hill I'm willing to die on, the reason why I rant about them all the time, is that, and the thing I stand by, they are not complicated. The thing you know about them are wrong. They are actually easy. Monads in programming are a simple programming answer. They're the name we give to a simple programming answer to a simple programming problem. That's it. So why the problem with monads? It's twofold. The first problem with monad is the Haskell syntax. Because why do people try to learn about monads in programming? 90% of the time, it's because they arrive at Haskell from another language, and they're like, well, Haskell makes use of monads, let me look them up. And monads, despite not being complicated, use a bunch of Haskell syntax. And if you've never used Haskell before, Haskell syntax is weird. It's a bunch of operators, it's a bunch of anonymous lambda functions. It's weird. So if you arrive at Haskell from other programming languages and you've never done any Haskell and you try to learn monads too quickly, your problem is the syntax, not the thing that they are. Like, imagine you've never touched a programming language in your life and someone tries to teach you multiple inheritance. No one claims that multiple inheritance is horribly, impossible to understand. It is complicated, but no one puts them at the same level as monads, right? But if you start with that, you're going to have a problem. That's part of the problem with monads. But the real problem with monads, the real problem is their name. The name is fine. I'm not arguing for it to be changed. But the problem is the myth around the name. Like, if I say monad, there is one sentence that immediately comes to you, regardless of your level of Haskell, and you can say it with me, monads are just monoids in the category of underfunctors, what's the big deal? And that sentence is bullshit. Okay, I've moved the microphone back. I've been in the red for a few sentences now. That sentence is just, as far as programming is concerned, that sentence is bullshit. It is wrong. It is irrelevant. It doesn't apply. And the real reason why, and the thing I want you to understand is this. The monads of programming and the monads of category theory are not the same. They share some DNA, obviously. They share a name. But they are not the same. Let me show you an example of what I mean using another thing that uses the same name across different domains. Let me introduce to you this mathematical function f here. This is a math function. This function f, to a value in n, its domain, the set of all integers, associates a value in n, its codomain, the set of all integers. To a value x, this mathematical function f associates the value x plus 1. Great. Let's now talk about a C++ function. This is a C++ function. It takes no argument, it returns no value, it performs side effects. We are using the same word, function, to talk about this one and to talk about this one. But I hope you realize that the math function and the C++ function are not the same thing. What's the derivative of this one? What's the integral of the C++ function? What side effects can the math function perform, right? Those sentences are nonsensical. There is no derivative of a C++ function. Math functions don't perform side effects. We very naturally understand that a math function and a programming function are related things. They share a name, they share some common DNA, common ancestry, but they are distinct things. We don't take for granted that the definition of function in math will apply to a function definition in C++, say. We understand that those two things are distinct. The same thing is true for monads. The monads of category theory are one thing. the monads of programming are another. And trying to apply category theory definitions of monad to the programming ones is wrong. So the whole sentence, monads are just monoids in the category of underfunctors, I don't even know if it's true for category theory monads. To my understanding, it's incomplete, but it doesn't matter. It doesn't apply to the programming ones. It's irrelevant in the realm of programming, which is why that sentence annoys me so much. So, what are monads then? What's the point? Well, to talk about them, there's a few things I need to talk about first, like lay the ground before I can actually talk about what they're used for. So go with me on a long tangent, if you don't mind. The thing I have to talk about first is interfaces. And you might know interfaces by a bunch of different names. A lot of languages, object-oriented languages, tend to call them interfaces. Rust call them traits. Haskell calls them type classes. JavaScript call them prototypes. All of those terms are more or less the same thing. There's, of course, differences between what each language mean by each of them, but they occupy kind of the same space, right? They define a contract. Like a type is enumerable if it provides this function. Usually for enumerable, that would be like, give me an iterator at the beginning of the list or whatever. And if a type is enumerable, then you can write generic code that works for any type that is enumerable, regardless of what actual type it is. In Haskell, I can write a function that works on any thing that supports any number that has the plus function. In C#, I can write a function that works for any enumerable container. In Java, I can write something on any serializable type. You can write generic code. I suppose if you're watching the stream, you know what an interface is. There is a case that I think is interesting, and that is relevant for this discussion about monads, which is when a language itself is aware of the interfaces of the language itself. What I mean is, when you can extend the syntax of the language by making things work for any type that matches an interface. An example of this would be C#. In C#, you have the enumerable interface, which is the interface of types that can be enumerated, usually containers. Any types that is enumerable will work with the for loop of the language. So the for loop of the language is made to work with any type that implements the interface. So if you create your own type and you implement the interface, it will work natively with the for loop. So you can extend the syntax of the language to any type. Hello, everyone. You can extend it to types that support that interface. Another example that I think is also interesting is JavaScript. Surprisingly, you will rarely hear me praise JavaScript, but here it provides a good example. Async and await stuff. Because in JavaScript, I'm going to put it in the comments since I'm still in a Haskell file. If I do something like result is a fetch of, I have no idea, google.com, I'd say, fetch does not block. It returns immediately. So since it returns immediately and performs the fetch in the background, this result thing here is a promise. So what do I do with a promise? Well, if I want to get the actual results, this is a promise, I can do a await of the promise. I need to remember semicolons. I can do this. And await is a keyword of the language. That's important. We'll get back to it. But if I already know ahead of... That's a good point. Yes, I could have picked any other domains there. But if I already know ahead of time what I want to do with the result of this, I don't have to block and then do something. I can choose to instead do I can't indent because this is not a JavaScript file. I can do then and give it a callback. For instance, then I have no idea, fetch first link, something like this, that may itself return a promise. So this whole thing still gives me a promise. And if I know what I will want to do afterwards, I can do a then that will, I don't know, click first add or whatever. something like this. You know what I mean? Every step, I give a callback that goes and does the next step, and this whole thing gives me a promise. And at the end, to get my result, I await the resulting promise. The interesting bit about this is in the history of JavaScript, there's been more than one promise type. There's been more than one type that implements promise. So for the await and async keywords, they didn't want them to work with only one of the types. So they did the exact same thing I was talking about, which is why I'm mentioning all this JavaScript thing, which is await and async don't work on a specific type. They work on all of the types that have the same interface. In JavaScript, it's not an interface, it's a prototype, but you get the gist. It's called thenable in JavaScript. It's the types that provide this then thing, because providing then is enough. But if your type provides then, it is compatible with the await and async keywords. So this idea of, okay, interfaces, prototypes, traits, type classes, whatever you want to call them, they are things that allow you to write generic code. And in some languages like C# and JavaScript and a bunch of others, Rust does that quite a lot as well. They allow you to even like extend the language by writing keywords and language constructs that rely on the interfaces. I tempted to do a quick side note. There is a thing that I like to talk about as well that is semi-related, and it's this then thing, because this then thing that JavaScript does for promises is quite smart and shows up in a bunch of different places, including in places you don't expect. So, okay, indulge me in a side note to the side note. Let's talk about then for a second. Because what then does is this whole thing is a promise of some value, probably like an HTTP result or something like this. And this then takes the value within the promise and gives you the next thing. What then does is smart, however, is this: if this whole thing gives you a promise, rather than giving you a promise of a promise, it collapses them into a promise. If I were to write this in Haskell type notation, because I find it the more readable, and since I'm going to be talking about JavaScript, Rust, and C++, using shared notation is going to be easier. I will happily talk about AI and the future of coding after I'm done with the side note, to go back to the monad side note rant, and then I'll talk about it. If I were to write the type of this then thing using Haskell syntax, it would be something like: I have a value A in a promise, I have a callback, which is a function from A to promise of B, so takes the value inside the promise when it becomes available, applies the function to it. That gives me a new promise for a new type, B, whatever that is. A could be int, B could be string, A could be HTTP response, B could be session cookie, something like this. And the whole thing gives me a new promise of B. It combines the previous promise, the callback, to give me the thing. Now, why do I want to talk about this then thing as a side note? It's because this pattern shows up in a bunch of different places, in different languages, for different reasons. For instance, in C++ and Rust, the thing is, TypeScript might be a better example. I don't know enough TypeScript to be able to be able to talk about it. I know about like await async in JavaScript. I have yet to write a single line of TypeScript in my life, but it would probably, the logic would be the same, but there might be some more interesting examples there. I need to learn TypeScript at some point. Yeah, this pattern also shows up again in other languages for other things. And in C++ and Rust, it shows up for the same thing, which is the option type. That if you know Haskell, you might know as the... oh yeah, that looks pretty clean. In C++ and Rust, my Rust, it's been a long time. But in Rust, it would be something like, and then that takes an option of A and a F and an F, and returns an option of B where F happens to be Fn once from A to option B, something like this. I don't remember the syntax of of, or is it something like that? It's been too long since I've actually done any Rust. It's been like a year, so my Rust is, pardon the pun, a bit rusty. But it's gonna be something along those lines, which is why I'm using the Haskell syntax as like the glue binding all of them. But yeah, the logic, the where then shows up in C++ and Rust is on option, which is again the same thing as the. Okay, fair, you got me there. It's the same thing as the Haskell maybe thing, which we can use for like lookups or something like this, where you may not have a value. And the thing is, the logic is kind of the same. If you have a function that gives you a, let's say I'm in C++, and I have a function that gives me a lookup user something, and I give it 42 because, and if this is an option, and here I would have to do like if not x return or something. Yes, Haskell being interrupted. I'm currently in a side note in a side note. I'll be back to regular Haskell programming in a second. Like you would have to do something like this. You would have to manually decide how you want to handle the thing, right? It's the same thing as here. After a fetch, I can do an await. But if I already know how I want to use the value, I can just use a then. C++, Rust have the same thing for option, where I can do on this thing, if this gives me a maybe an option, I can do an and then and give a callback here, and then do an and then and do a callback here, and so on. If I apply Haskell syntax to this, the and then of C++ and Rust has this shape, which is option of A, takes a callback from A to option of B, and gives me an option of B. And that's the thing I find neat about this pattern, that it shows up here in JavaScript for async stuff. It shows here in C++ for and Rust for maybe stuff, which is fun. It shows up in a place you also might not expect, which is in Java. Because what if instead of like the value will be available at some point in the future, or the value might not exist, what if it were there might be more than one value? Well, you would get something of the shape list of A, function from A to list of B, that gives you a list of B, applies that function on all of the elements of the list A, get a list of B, brings it back down as a list of B, kind of like then here gives you a promise of a promise and brings it back to a promise. In Java and Scala and other Java-like languages, this is called concat_map, or flat map in some languages. But that's the same shape. And I think that's fun. Do I want to continue on the and then stuff before going back to monads? There's one last thing I want to showcase. One last thing I want to showcase, and that's gonna bring it back into monads. That's gonna be useful because I started to talk about monads, talking about this whole interfaces that the language is aware of to extend the syntax. I can bring both of those together. I can bring the side note back into the side note by showing you maybe in Haskell. Because let's go back to my maybe example. I'm going to write this in Haskell. Let's assume I have, let's go back to an old example I used years ago, 8 years ago now, when I was teaching Haskell to beginners. Let's assume I have a lookup user function. It takes an int and gives me a maybe user. Whatever user is, however that function is implemented. It's unrealistic because it doesn't seem to be performing side effects. Bear with me, this is an example. Let's assume I have a lookup phone number that, given a user, gives me a maybe phone number. And let's say I have a lookup parent function that gives me from a user, gives me a maybe int, which is the ID of a parent user if there is one. Now, if I were to try to write, it's going to be ugly. It's fine. If I were to write a lookup parent phone number function, it would take the ID of the user and give me a maybe phone number. And this is going to be, again, an example similar to the JavaScript fetch thing. So I have a user ID. How do I do this in basic raw Haskell? Well, I call lookup user on my user ID. And it gives me either just a user ID or nothing. So I can do a case. So I can do case of, if it's nothing, my whole function gives me nothing. If it's just the user, then I can call lookup parent on the user, right? Which gives me maybe a user ID. So I can do a case of, if it's nothing, I return nothing. There we go. If it's just a parent ID, then I can continue. I can do a lookup user on the parent ID, and again do a case of on the result. If it's nothing, I can return nothing. If it's just a parent, I suppose, then I can do a lookup phone number of the parent. And that is how you chain computations in the maybe monad. At every step, you have to be like, God damn it. You have to stay, well, like, did I get maybe at the step before, or did I get just at this? And how do I chain things, basically? Ignore the fact that I mentioned maybe is a monad that will be relevant later. But the point I want to make is this pattern is, at every step, I have to do some manual checking, and the type could be doing that checking for me. In the same way that, again, for promises, you can use this then, rather than at every step doing await and calling the function ourselves. It turns out that Haskell, of course, has an equivalent to this and then thing that C++ and Rust have for option, for maybe. So we can rewrite this whole thing as being, well, actually, I'm going to keep the old version for comparison. I can rewrite this as being, I'm just going to scroll this, there we go. I do a lookup of the user ID, and then I introduce a function, a callback function, that takes the user, and, which is this thing, and then does a lookup parent of the user, and then gives a callback that takes the parent ID. And with it, we do a lookup user of the parent ID. And then we give a callback, which is going to take the parent. And what do we do with it? We do lookup phone number of the parent. This function is the same as this one, but we trust, since maybe implements like the provides and then interface type class in Haskell language, we don't have to do all of this unwrapping, rewrapping ourselves. We can trust maybe to just like know how to go from one thing to the next. We just provide the callback. And that is indeed somewhat weird Haskell syntax. But to tie back to where I started to, well, I hope I'm not going to lose everyone there. But yes, to tie back with where I started, the side note within the side note, the whole thing about we can use interfaces to extend the language, Haskell has that. And indeed, as mentioned, it is the do syntax. The do syntax is syntactic sugar that Haskell desugars into something that makes use of the and then interface. Basically, if we were to rewrite this function again, a third and hopefully last time, and if we were to look at the shape of what we are doing, right? At every line we are doing a value that we are doing an expression that gives us something within the maybe. And we are using and then to go from one line to the next. what if we had some way of removing this verbose and then on every line? Well, what could it look like? If I remove some of the syntax and I do this, for instance. This is not valid Haskell syntax, right? This is just what it could look like. Well, if it looked like this, we could also drop the indentation. This would be like, we can see how the compiler could go from this to this, but this is a lot more readable, right? Well, that is basically what a do block is. A do block is, the difference is that the thing comes first. But this is what a do block is. It takes this and sees, oh, all of those things return something in the same kind of value that wraps another value. Like in this case, all of them are maybe. Okay, all of those things, like that type provides and then. All of those lines can be chained into one another using and then, and it translates this into this. In the same way that await and async in JavaScript work on any type that has then, do blocks in Haskell work on any type that has and then. And in the same way that any type in C# that has enumerable works with the for loop construct of the C# language. Okay, so that was a side note within the side note, because I think this and then pattern to be interesting. But my whole point is about sometimes a language can make use of an interface to extend a part of the syntax, some keywords, for something that is useful in the language. Now, before I go back to talking to monads, there's one thing I have to mention because it's funny. Because, again, in JavaScript, the name of the interface, the prototype for things that provide then is thenable, which, you know, it is able to do then. That's a pretty straightforward name. But the name in Haskell for the interface, the type class of things that provide and then, it's Haskell. Of course, it's a mathematical name. Does anyone want to guess what the name in Haskell is for things that provide and then? I'll give you a second and get a drink while someone... Applicative is a very good guess. You're very close. But yeah, the name of... because if I write it down, what does it look like in Haskell? Well, the thenable thing, a type is thenable if it provides and then, which is again takes a value a in that m, which is maybe, promise, list even, as we have seen, and takes a callback that gives us the next value in that thing and performs the chaining. That's the shape we have seen for, you know, the then of JavaScript, the and then and C++ and Rust, the flat map of Java and Scala. That's the shape. Except since it's Haskell, again, first, it's not called and then. I've used and then here for readability. It's actually an operator, because of course it is. It is this operator, which kind of looks like the Haskell logo a bit. But of course, yeah, the name of this is not thenable. It is a math name, and it is monad. And now you understand my frustration. Now you understand my frustration. Because the idea of thenable is an idea that anyone who's done anything async in JavaScript has used. Using and then in C++ and Rust is a thing that C++ and Rust developers do basically every day. Using flat map in Java is a thing that anyone who has written any Java has done. The concept of we have an interface for that shape of solution, and some languages like JavaScript are able to make use of that interface, is not a complicated concept. And you'll notice that, especially if I write it using and then here, does that definition says monoid? Does that definition says endofunctors? Does that definition mention categories, perhaps? No, this is an interface. This is an interface for the types that provide and then. That's it. That's what a monad is. Of course, I don't want to like deny the fact that things can get complicated. You can make some very complicated monads. The syntax can get complicated. I don't want to deny that. My point is, the concept of what they are is not complicated. Monoids are a lot simpler. Partly because the monoids of math are a lot simpler and the monoids of Haskell are a lot closer to the monoids of math. A value is a monoid if it provides two things, a default value of that type and a way to combine. Is it mconcat? No, append, which is something that takes two value of the type and returns a new value of the type. That is very abstract like this, but in math, for instance, integers form a monoid with the rules that I expected is this is the neutral element of this function, and this function is associative. So if I were to write it down, that means mmpt, and there's an alias often for other reasons. This mappend is often written as the operator like this. And the rules that are expected of this is basically mmt and a is the same thing as a, and a and mmt is the same thing as a. Mmt is the neutral element of mappend, and I've already made like a thing about monads like this, and I want to make more videos to explain stuff like this because I think it's not that complicated and it's often poorly explained. But to continue with this, and the last part is it needs to be associative. So A and B concatenated with C would be the same thing as A appended at the beginning of B and C. And like as you can see, for integers, addition with 0 matches this, because 0 is the neutral element and addition is associative. For integers with product also, because product with one I have to read this one out loud for the people who see this on YouTube later, but a monoid is just a lax monoidal functor from the terminal category into set. What's the problem? And yeah, this, you see, like, this is a fairly straightforward programming definition, but you can make it as arbitrarily complicated if you want in the realm of math. But it doesn't make this more complicated than it needs to be, right? And for product, A times B multiplied by C is the same thing as A times multiplied by B times C. Another example of monoids would be strings, because empty string and concatenation matches this. But yeah, monoids, a lot simpler. There is a way in Haskell to make a link between monoids and monads, but it requires showing some syntax that I don't want. Like, since again, I think the main problem of monads is the Haskell syntax, I don't want to showcase that syntax yet. There is a way when we talk about the type class laws, but maybe later I'll do that. Now, the thing I want to do with this, since again, the whole point of monads is it's the thenable class, it allows us to build computations by chaining things in kind of like an imperative way, basically. I want to write a monad for this project, but instead of writing it by using existing stuff, let's write it from scratch. And that way we can see what a monad, like how it works. Before that, since the question has been asked about AI, a 30-second thing I will say, I am strongly ethically opposed to the use of AI in its current shape. I never use it. I will never use it in its current shape. I do not use it for any work project. I will not use it for this project. And that's for a combination of reasons. A lot of them are ethical reasons, as in, even if the technology was good, even if it worked, even if it had no downside in the way I do my work, which I think it has, to be clear, I would still not use it in its current shape, because in its current shape, it is deeply, deeply flawed. There is the environmental cost. There is a lot of ink has been spilled on the water cost of AI, and that is very hard to quantify. It's probably true that a given AI query doesn't use a lot of water, but at the same time, it's also true that data centers use a lot of water, and more data centers are being built just to anticipate supposed AI demand. And those are often built in places where water access is restricted. And where they are being built, they are creating water shortages. So, it's not as simple as saying, oh, you're using a query, therefore you're using water, but they are being built in places where resources are being already a bit strained. Another way to see the environmental impact, most of the big tech companies have commitments to reduce their carbon footprint. Google, for instance, famously has a goal to to be carbon neutral in their data centers by 2030. Over the last 2 years, most tech companies have increased their emissions because of the increased demand on the spending on data centers and everything to try to be able to accommodate the demand they anticipate. Google, for instance, in 2024, increased their emissions by 30% instead of continuing to go downwards towards the carbon neutral thing that they're aiming for. So there is a direct environmental cost that I'm not okay with in the first place. There is ethical is complicated to describe, but there's also a labor issue, right? I say talking about copyright is complicated. Copyright is a very difficult subject, and I don't want to come out swinging with a non-expert opinion. Copyright is all good or all bad. It's more complicated than that. I will say that there is definitely a double standard in the way it's applied, where if I as an individual put one Nintendo game for to share with friends on a website, I face 30 years in prison and millions of dollars in retributions. But if a company like OpenAI scrapes the entire internet, every single movie, every single Facebook post, every single YouTube video, every single thing they can get their hands on, they get a slap on the wrist at best. And you could argue, well, maybe the model of copyright is not good, and maybe the fact that maybe all of this information should be free, right? But at the same time, that doesn't apply to us. It applies to them, not to us. And they're using all of this stolen, unethically obtained data to train things that then replace the people who produced the thing it was trained on in the first place. Artists are losing their jobs more and more, being replaced by AIs who are not as good, but that managers are convinced can replace them. So there's also this big ethical thing, right? The ethical concerns go beyond this, because there's also the problem of who controls those AI models and what are their intentions with them. We see this more with XAI, but that's not a small one. When people are being told that those AI are very smart and reliable and source of truth, and then you have the owner of the AI decide what is true and what is not. This becomes an instrument of control. This becomes an instrument of propaganda. We have seen this on Twitter with Grok becoming Mecha Hitler, right? Because it was instructed to be politically incorrect. There is the problem of who controls those models and what they use them for. And at the moment, those models are a lot more about trying to gain control than they are about helping people. To put it in more blunt words, AI is currently, as it is, part of the techno-fascist project that is rising in the global West, the global North, I mean. So that's why even if AI worked, I would not be I would not be enthusiastic about using it. I would have my reservations. But there's a problem that it doesn't. Before talking about why it doesn't, one last thing as well I need to mention, which is the social cost of AI. We have never really encountered in the history of humanity something that convincingly talks like a human without having some kind of intelligence behind. That was the whole point of the Turing test that we have kind of proven to be obsolete, which is that if the thing is able to carry on conversation, it must be intelligent, right? And no, AI models are not intelligent. That's not how they work. That's not what they are. But a lot of people are convinced that this thing that talks to them is, which is why there is a rise in what has been described as AI psychosis. It's not a formal diagnosis yet, but it has been proposed as a term as the phenomenon keeps happening. There is several, I think we are like 5 lawsuits total against OpenAI at this point for people who died because of, I mean, yeah, I mean, one conversation casual, the problem is capitalism, right? You know the meme? That's exactly that. The problem with AI is capitalism. But like beyond that, there's also again those tools as they are today are also creating a lot of psychosis of people who end up trusting those things. There's that YouTuber whose name I forget who did an experiment of like, okay, I'm gonna make a fake scenario and I'm gonna trust everything ChatGPT says. And ChatGPT ends up like basically telling him, isolate yourself, cut your contacts, go away, wrap yourself in tinfoil. And it's like, yeah, you can see how someone who doesn't understand how the technology works will be sucked in. This has a cost. There are several teenagers who lost their lives by being told how to kill themselves by ChatGPT, right? There's a social cost to those things. And to cap it all out, on top of the ethical issues, the environmental issues, the labor issues, the technofascism issues, the psychosis issues, it doesn't work very well. Those things are not smart. We've known for a while, and several researchers in the field will tell you, we will not build AGI on the back of LLMs. That's not what they are. They're glorified autocomplete. What they do is impressive, don't get me wrong. It's pretty fascinating that purely building a statistical model of language gives something that works that well. But it's not the same thing as being intelligent. In fact, models at the moment on like topics of like news and things, they have like a 50% hallucination rate in some cases because, you know, a probable answer is not the same thing as a correct one. So if you have something that's not guaranteed to give you the same answer for the same output for the same inputs and hallucinates 50% of the time, how reliable is that thing? The answer is not really. So for code, well, the problem is like, you know, the whole point of having someone who's an engineer write a thing is they've spent some time thinking about the thing, modeling the problem, creating a mental model of how the thing works and how it might evolve, what kind of errors it might encounter. When you delegate that to a machine, you lose all of this. You've auto-generated the thing. Regardless of how good it is, you no longer have that state in your mind because you haven't done the work. You haven't done the process. Like if you've just generated the thing, you haven't built this mental model. It is basically tech, it is generating tech debt. You might argue, that's like some people do, like, okay, but not all code is maintained, right? Like a lot of code is written once, run twice, and then thrown away. Why not generate it? A study of open source developers that included a lot of experienced developers has asked them to try to like predict if they would be faster on some tickets using AI. They all claimed like, yeah, it's gonna help me be a bit faster. They were 10% slower. Experienced engineers knowing the project were slower using AI because they had to go and fix the mistake that the models were doing. It's that simple. Again, statistically likely is not the same thing as correct. So to sum up, we have a technology that like is not that good at what it does, has an extremely high error rate, makes you less good at the thing you're doing and basically replaceable, and basically pushes the problem down the line because you're not doing the actual work in the first place, while creating some environmental issues by constraining resources, emitting pollution. I haven't mentioned that before, but a lot of data centers emit a lot of pollution. XAI data centers are polluting disenfranchised neighborhoods, while also participating in the rise of techno-fascism in the West. Like, what's to say about this technology? Which is why at this point, at this current point in time, I refuse to use AI. I will not use AI. Do I see a future in which it can be used? Yes. I think if we manage to reduce the cost of inference, the cost of training and everything, and we train smaller models on ethically obtained data, and that is done by companies that don't have profit motives linked to the US war machine, I could see that being useful for a few things. One thing I think it's very useful is to solve the blank page problem. Starting a project is difficult, but generating a scaffolding that you then iterate on, generating like a hello world kind of thing, thousands of examples across all projects and all languages, that's something that an AI could be reasonably good at outputting. Something that statistically looks like a scaffolding for a given project. Yeah, it would probably be pretty decent. But that's, a small use case and not the AGI thing, right? So yeah, and on top of this, AI is probably going to could create the worst economic crisis since 2008, or maybe even worse than 2008, because of the spending that is currently happening in data centers that is just not going to turn a profit. So, for all of those reasons, AI not really convinced and actively hostile. In my line of work, I'm lucky enough to be senior enough that I think I will probably be safe. I've seen several people in comments mentioning of like actually they prefer hiring people who have had experience before ChatGPT and other models became a thing because they tend to have better retention with people who are not using LLMs all the time. So I'm not too worried. But there's definitely like what's going to make it difficult for our industry is a lot of junior developers are going to be replaced by LLMs, regardless of whether LLMs are good. That's a management decision on the technical decisions. But the problem is, where do senior engineers come from? They come from junior developers. If junior developers can't get jobs, you get fewer senior developers, right? So there is a long-term risk, I think, for the industry by trying to replace junior people by AI and then preventing them to develop the skills they require to become more experienced. Again, if the bubble pops and this whole thing crashes, maybe there won't be an issue. But also, yeah, like this is just machine learning on Markov chains. None of this is new, right? But yeah, that's my thoughts. Ways is that side note 3 in today's thing? But yeah, that's my thoughts on AI. I cannot wait for the bubble to pop. When it does, it's gonna hurt because, well, the American economy is currently only held by the capital expenditure in data centers, and if it pops and all this is for nothing, the economy is gonna hurt really bad. And even here in Europe, we're gonna feel the consequences. But I think still, the sooner the better. Also, I forgot to mention, no one wants AI. AI is associated instead with negative consumer sentiment. When people see AI in a product, they think less of a product. When people hear that the coworkers use AI, they think less of their coworkers. AI has negative consumer sentiment. No one wants it, which is why it doesn't turn a profit. Anyway, NFTs are the future of art, and AI is unescapable. And I cannot wait to see. Yeah, I am so sorry for your situation. It's like, yeah, that hiring juniors at the moment is difficult. Anyway, to go back to something a bit more positive, let's and on the language thing, sorry, I'm bringing a bit of the scroll back. Yes, one thing I realized very quickly, something that everyone who has tried to use ChatGPT and other LLMs realizes very quickly: if you don't know much about the domain, it will sound very confident and will give you something that looks very good. But if you know about the domain, you will realize very quickly, like, nah, this is not really accurate. If you know a small language, like a very obscure language, try asking a LLM to generate some code in it. It will be completely wrong. Like try brainfuck, for instance. There are a lot of examples in brainfuck in the wild, but since it's absolutely not syntax like friendly to LLMs, any brainfuck generated by an LLM will be completely, utterly wrong. It will never be correct. Even the reasoning models, which are not actually reasoning, because again, those are not intelligent. Let's go back to monads. And to cap this, monads are not actually that complicated. They're just the name we give to the thenable interface, because chaining computations using and then is a very common pattern. Let's write our own. Let's write a type. Let's make it a monad. And for this project, the thing I need to write that is one of the missing things before I can actually compile this refactor is a diagnosis monad, which will look something a bit like this. Yeah, I mean, yeah, and the thing is, like, a small local LLM trained on data that you own for a particular thing, is it going to be very good? No. But is it more ethical? Yeah, absolutely. Actually, before typing it, let me show you what I want to do. I want to be able to do something where I have a function foo that opens a do block, which will be translated into calls to and then, because that's what do blocks do. And I want to be able to do things such as, this is pseudocode, when length args different from 3, report error, something like this. And then when, I don't know, name already exists, name emit warning shadowed name or something like this. I want to be able to chain computations that at any point might fail because we are emitting warnings and we are reporting errors. That's what I want to do. So what would that look like? I want to have some kind of diagnosis thing that will wrap my values of type A, whatever they are. So I can have like diagnosis int, diagnosis module, diagnosis whatever, that wraps that thing to add the context of what errors, what warnings have we encountered, and did we get a result? So this will be a, I'm actually on like, a new type. So this is going to be a type with one constructor. And what does it need to contain? For reasons that I will explain, I'm going to call this field run diagnosis. What is the value within our type? Well, it has to contain A, right? It has to contain the values of our type. But if it were just that, it would be kind of useless. Now, one thing we need to be able to do is we need to be able to short circuit, which means if we have something that throws an error, it needs to be able to, like, well, we can't continue trying to apply callback functions, does nothing. A classic way of doing this would be to use a maybe. So we use a maybe A, and every step in our computations returns either a value, just a value, or nothing. If it returns nothing, it means an error happened, and we have to short circuit. Great. But we also want to keep track of some state, right? We need to keep track of what warnings have been emitted, what errors have been emitted. How do we keep track of state in Haskell, a language that doesn't have mutable state? Well, if I were to write a function that, like a pure function, no monadic stuff, that does this, I could do something like this. Analyze function call, and it takes the previous state, and it takes information about the function call, function call info, I don't know, and it gives me the new state that has been modified, and maybe the result of my thing, which in this case would be, I don't know, a resolved function call or something like this. It takes the old state as an argument and returns the new state in the response. So for instance, if I were to do something like this, and maybe I don't know how to, like, I would have to invent a bunch of other functions to write this, but you can see the shape of it, right? We take the old state, we return the new state. Well, this is going to be the same here. We're going to have some state in the input, and our result will be the new state and the value. This will be the shape of a step in our function, in our diagnosis monad, in the same way that this analyze function thing was from state and some information to state and maybe result, basically. what is our state going to be? Well, that's going to be our diagnosis state that we're going to introduce. There are ways I could do this without writing all of this myself. But again, I'm going through the steps to showcase what it looks like. Our diagnosis state will be a record that will contain, I think we only need two things. Did I move? I haven't. Actually, I might move this file. Do I have? That's fine. In my old code pre-refactor, if I go to analysis old, no, I'm not aware of that syntax at all. Is it, so you say it's in lean? I'm not familiar with lean. That looks interesting. No, there's not really an equivalent of that. Here in this old file is where I have all the stuff from before. Here is where I'm not gonna copy all of this because a lot of it is wrong. I might just copy this and put it in here. So that is a message, and a diagnostic is something that contains a base name. Do I have? Wait, where do I have the typo? Well, thank you for tuning in. And yeah, I'm super late on uploading things to YouTube, but I'll try to upload all the streams to YouTube as soon as I can. Sorry about the delay. I have like a month back. In a type definition. Yeah, indeed. Thank you. Good catch. Which actually I'm gonna actually probably. No, it's fine to keep the whole. I'm happy. I'll make a clip. I'll make a clip of both the monadic stuff at the end without the AI part and the AI part in the middle as a separate clip. I'll try to do all of that tomorrow, hopefully. Next time I stream, I'll try to have it. Yeah, since tomorrow is Tuesday and it's my usual stream day, I'll try to have all of that uploaded to YouTube as clips by tomorrow. It's always uploaded to YouTube, but I'm sometimes very late. And in this case, none of the streams of last week are on YouTube yet, but they have been uploaded, and I just need to actually just like label them on YouTube and put them there. I'll do that tomorrow morning probably. So yeah, diagnostic will be what were we trying to compile when this happened. This could be a constant, a function, a struct type, whatever. What location, so where in the file, what row, what line, and then the message, which is this big thing that we're going to have to rewrite. Half of it is wrong now post refactor, but that's not the point. The point is the diagnosis state in our diagnosis monad will be something that keeps track of all the diagnoses we have emitted, either errors or warning. So this is going to be all messages, I suppose. Well, not all diagnostics, which is going to be a sequence of diagnostic. And I'm going to use a sequence immediately just because I'm going to do append at the end, and therefore I really don't want to use lists for this. And I think the only thing we're going to need to know, we're going to have some recovery mechanics in this. I can't type. I've been programming for 2 decades and I still can't type. Which is, as a side note to the monad thing, one thing that exasperates me so much is like people think monads are complicated. I understand them. If I understand them, anyone can understand them. Because I'm not very smart. But back to this, I think the only thing we need is, since we're gonna be able to like do a try thing and try to recover from an error, like analyze this thing, and if it failed, well, we can still try to resume. We still want to be able to smart. Yeah, exactly. We still want at the end to know, well, okay, we've tried to recover, but we don't want the computation as a whole to succeed if at any point there was an error, right? So I think we just need to keep track of like was there any error at any point? Which I suppose I could do by iterating over the list of diagnostics to check if any of them is an error, but that's a linear search, so might as well just also carry a boolean, which is any error, which tells me whether any of the things in this is an error. Okay, so we have our diagnosis, which is a thing, a step in which is given a previous state, return the new state, and maybe a value if that step succeeded. We can make this thing a functor to start with. So that thing is a functor. What is the requirement for this to be a functor? There's only one. It provides fmap. What is fmap? Fmap would be... Yeah, there's so many different kind of containers. Like, I mean, that's true of a lot of languages. A lot of languages have different containers with different trade-offs. Lists are everywhere in Haskell because they're very nice conceptually, but they are single linked lists, which in terms of performance is absolutely horrible, which is why sequences that work basically the same, like at a very high level in terms of like how you use them, while being very different internally, have like much better performances. So the shape of fmap is, it's a map. You've seen maps, right? It's like, I have a function from A to B. I have something that has maybe some A's inside, a promise of A, or a list of A, or a maybe of A, or in this case, a diagnosis of A. And I return a diagnosis of B. So I apply the function to the value within the context. So how do we apply a function f from A to B to a thing that is a diagnosis A? Well, I have this diagnosis value here. What I can do is, if I can get a function, my step function, by doing run diagnosis on this diagnosis. So I use this thing to get the field of this shape. And again, what I want to return is a diagnosis, so something that has this shape as well. So what I need to return, stream uploads. Yeah, the only thing is I try to keep clips on Twitch, but Twitch has a very limited amount of storage, and I'm already quite close to the limit, which is why I upload all the raw stuff to YouTube. I'll look to see if I can have a way of just as subtitles. Oh, okay. I'll look into that. That would be good. And yeah, possibly. But you can do a highlight, which is different. So here, okay, we have our step function. We have our f function from A to B. And what we want to create is a new diagnosis, and I swear I can type, that has this shape, but returns a maybe B at the end. So this will be a function that takes a old state. And what does it do with it? It applies the step on it. And that gives us... Okay. That gives us... What does that give us? That gives us the new state and the maybe B. So we can do... Actually, I'm not going to do this let in. I'm going to do this. So that's new state maybe result is the result of getting this function and applying it to the old state. And our result is the new state, unchange, and fmap of f on the maybe result. Okay, that's a bit verbose, but the point is now, if I have a diagnosis of int I can do fmap show on it, and I'll get a diagnosis of string. Fmap is now implemented on this thing, where we do get similarly still a diagnosis that, given some old state, applies the step to the old state, gets the new state and maybe the result, and transform the maybe result by applying the f function inside the maybe. If I wanted to be super explicit, I could do something like case here of the maybe result of, nothing, just some a, apply f to the a. But that's the same thing as fmap f on the maybe result, and smart observers will notice tuples are also functors. Therefore, I can rewrite this as being an fmap inside the tuple and an fmap inside the thing. That is an fmap2 of f inside this. And if I wanted to go a step further, I could even remove this old state stuff. This is fmap2 of f inside this. Given some state, apply this state function coming from the diagnosis A, and then fmap to f inside it, and there we go. We've made this a functor. Now, we can make it an applicative. What is required for applicative? What is required is pure, which, given some a, creates a diagnosis a, so puts the value inside the context. For us, that's very easy. That's a so pure of some value a is going to be a value of type diagnosis that, regardless of what the state was before, leaves it completely unchanged. So given some old state, leaves it completely unchanged, but gives us that state and the value a. So it will be old state, unchanged, and just a, which we can rewrite as being this, basically. Or even, I think this is enough. This is a partially applied function. Yeah, I think that's correct. There you go. Which I could probably even rewrite as... Nah, it's going to be too complicated. I think this is fine. And the other thing that applicatives require... So this is the part where there's a bunch of Haskell syntax, which, again, what we're doing at every step might be complicated. And that's the part where beginners with monads get really, really confused, because there's a bunch of functions where the shape is complicated, which is why when I was talking about the and then stuff, I was really trying to focus on what problem are we trying to solve? Here, there is a bunch of syntax that gets in the way. The other thing we have to do is write for applicative, we have to write apply, which is an operator that looks like this. And its type will be, well, I have a function in my diagnosis, because, diagnosis is any type A. It could be anything, including a function. So I have a diagnosis from A to B. I have a diagnosis A, and I want to make a diagnosis B. And that is going to be... pure is kind of a constructor, I suppose, yeah? I mean, for some of the types, it's literally a constructor, in a sense of for maybe, for instance. Actually, let's start with that. It's going to be a lot easier. Let's start with implementing those things for maybe, so that we can see the difference. Those already exist, but we can still do it. Fmap for maybe will be the same shape, so it will be this. And so fmap, given some function f, will be a case of if it's nothing, return nothing. If it's just some x, return just of f of x. Excuse me. And I'm almost tempted to do it for state as well, but we're already doing it for state. It's not that more complicated. And for applicative, pure is, is just just, that's putting a value in the maybe, and apply if we have maybe a function, a maybe a and a maybe b, then apply it's going to be a case of f of just a function, well, maybe f. If it's just a function, then we can do f map of f on a. We could write the case here, but there's no need, which is like, you can see why applicative depends on functor. And in the case of nothing, well, we return nothing. Our case for diagnosis is going to be a tiny bit more complicated because we have more things to do. But given a diagnosis function, and that was not correct, that is not correct, it's this operator. And a diagnosis value, what do? We need to make sure we route the state properly through all of this. So first, we'll get at the end a diagnosis thing, which starts with the old state. And what we do with it is we get, so that I can get state 0. I get state 1 maybe f by doing a run diagnosis of the df and giving it the state 0. And here I want to short circuit if that didn't work, so I can do a case maybe f of, if it's nothing, this whole thing will return state 1 nothing. And otherwise, if I have a function f, then I can do the same thing again. When I do state 2 maybe a, by doing run diagnosis of the diagnosis a, giving it state 1, and in case maybe a of, if I have nothing, I return state 2 nothing. But if I have just an a value, I can return the state 2 and just f of a. Okay. This can probably be simplified using some properties of maybe and everything, but you get the gist. Now, actually, let's see. No, actually, let's do monad first, and then I'll go check how state is implemented, because it's implemented with the same logic as this. Last but not least, what is required for monad? Well, for maybe, that is just implementing and then, which you know as this operator, which is, well, fmap2 here, the problem is like, we need to do this in the case, this probably be a traverse, a thing of maybe, but I don't have any problem with writing it very explicitly like this for this core function, since everything else will be translated into functions using this at the end. I don't need to do that. In this case, this and then thing for maybe has this shape. And here, this is therefore going to be, I have some maybe a, I have a function f. If my maybe a is nothing, I return nothing. If it's just some a, I apply f to a. That's it. And for diagnosis, it's going to be easier than... oh, sorry. I didn't get... I saw that I thought we were talking about fmap2 like we have used in the case of functor here. Yeah, the type of fmap2, that's not a thing that exists in the prelude. It's a thing I have introduced myself in my prelude here. And fmap... Oh, fmap3 is this. Fmap2 is indeed, if I have an f of g of a, I make it into an f of g of b. That is fmap. Oh god, do I do a side note in the side note to the side? Yes. It's already on screen, I'm gonna hide it. You know of the dot operator, which is like the function composition thing. I have a function from b to c, a function from a to b. I compose them into a function from a to c, right? There is a fun thing where if you want to do a function which is, well, I have a function from C to D, and I have a function from A and B to C, and I want to compose them into a function from A to B, A and B to D, basically, by applying the first function and then the second, so composing a function of one argument to a function of two arguments. You can do that manually, of course. It happens to be that if you do dot, 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 you compose dot with itself. That is exactly the type that you obtain. That one is very fun. I use it. It is nicknamed the Blackbird in reference to a book about combinatorial functions. The Haskell Google style guide, there's not a lot of Haskell at Google, but the very little there is, the Haskell style guide explicitly forbids the Blackbird. I have it defined here. I really like it. It's very useful for like, oh, I do a lookup, which is a function of two arguments that takes a key and a map, and then I want to apply a function on the result, some fmap, some on nothing, something like this. Well, I can compose lookup with the follow-up function, basically using the Blackbird. That was a side note. Let's go back to, and yeah, fmap is 2 is fmap of fmap, and it's fmapping 2 levels deep. Fmap 3, fmap is fmapping 3 levels deep, and so on. Let's go back to this. So here in the case, it's going to be less complicated than this. I think this operator is the most complicated of them all. I'm just going to fix the comment that is wrong. For here, we're going to have a diagnosis A and a callback there. And what we're going to do is we're going to create a diagnosis, which is going to be our result. And it's going to take the state 0. And what are we going to do with it? We are going to obtain state 1 and maybe A by doing a run diagnosis of the DA and applying the state 0 to it. And our result is going to be, do we have a value A? In which case, great. The overall result will be the diagnosis B obtained by doing F, just A here, F of A. And if we have nothing, our overall result is just going to be the state 1 and nothing. And that's it. With all of that, we have enough. But now here's the trick. Doing this manually all the time is kind of annoying, especially since it's a bunch of callbacks and a bunch of complicated Haskell syntax. So I'm going to do this instead. I'm going to remove all of that. And I'm going to say here, deriving functor applicative and monad. And now I have that. And I don't have to write it myself, because the compiler recognizes this shape as something that's compatible with all three, and now I have access to them. Which means now I can absolutely do a function foo, which will return a diagnosis of int, let's say, and foo does a do block that does stuff. Except, here it can do like pure 42 or something like this, but we haven't seen a lot of things that we can do with this unless we manually call run diagnosis. So we will probably want to write functions that do things in this monad. Here is where I'm going to cheat a tiny bit. There are things I know I'm going to need, so I'm going to put them now. I'm going to make this a diagnosis T, which is a common suffix for a monad transformer, which is basically to say this thing will be on top of another monad, M, which means here the result will be in M, actually, which means we can stack diagnosis on top of something else. In our use case, this will probably be on top of IO, perhaps, because the root of our program, the main of our program, will be in IO, and we will stack diagnosis on top. Maybe not. Maybe diagnosis will be the root of the thing, and all of the stuff will be purely in memory with no IO. That would be better, but that is a possibility. And if I were to do that, I would say that diagnosis, the one without a T, is diagnosis T with identity. The mistake I'm making here is I'm giving a lot of details that are not beginner friendly for understanding monads. So this is why this is really the part 2. The first was like, what's the intuition for them? They're the venerable interface. Now this is the nitty gritty, which is difficult for beginners because we have so much details to go into. So I think that's really the distinction I would make. The intuition for them is easy. The nitty gritty gets complicated. And what else do I want? Yes, we're going to have to define what do we do with this thing, right? So I'm going to create a new class, which is monad diagnosis, which describes the capabilities of any monads that contains this thing. And what we're going to need is we are going to need something to report warnings, something to report errors, basically. That's going to be about it. So report warning, which is going to be given some diagnostic. Give me a diagnosis. Well, this is going to be for some monad M. Give me a unit in that thing, which means it succeeds, returns nothing. And report error that given some diagnostic returns any value. Since it will short circuit, it will fail, it can return anything because it doesn't matter. It will not give control back to the parent in a sense. Okay, so how do we implement this contract for this function, for this type here? Because of course, diagnosis T will be an instance of monad diagnosis. Diagnosis is T of M. I'm going to require a monad constraint here, but that's not a big deal. What that's going to mean is like, okay, well, diagnosis T is able to implement those functions. What do they look like? Well, report warning is going to be, I have some kind of diagnosis, and I need to do something with it that's going to be put in this thing here. Here, I could cheat and make this a monad state, but I don't want to. So we are going to write it manually. We are going to return a new diagnosis value, diagnosis T value, I suppose, actually. That will be something that takes the old state and modifies it to add this thing. So we are going to take the old state. I swear I can type. And we're going to return the modified state, and the value will be success and unit, because we have no value to return. And what do we do here? This is going to be modifying the state to change the diagnostics. I'm going to just quickly look at something, which is this syntax. There we go. I'm going to want to do a make lenses of the diagnosis state to be able to use lenses for this, because I'm going to want to say this is on the old state, I'm just going to say it's S in this case. I'm going to apply a lens function, which is the DS all diagnostics. I swear I can type. Sequence will be modified. Is it it's that operator by applying a thing, and I need to check what sequence is. It's this one. By adding at the end the value, the diagnostic D. So that complex stuff is just I'm modifying the state to add a diagnostic at the end, and the value I return as part of this step is just unit. Now we can do report error, given some diagnostic. And in this case, I'm going to write it slightly differently. It will be a diagnosis T that to some diagnosis state that I'm going to actually decompose here to have access to the fields. This will associate something which is again a tuple of new state and result. The result will be nothing. This computation has failed because it has returned an error, and the state will be modified. So this will be a diagnosis state that will contain the DS all diagnostics with that new diagnostic added at the end, and any error thing will be set to true. Okay, there is one thing that's not great about this design, and I'm okay with it, which is that since the diagnosis here is not the message but the thing here, you could use report warning on something called error, and you could use report error on something called warning. That's fine with me, especially since we might want to implement something like W error, in which case report warning would report an error. So, with that in mind, what can we do now? We can write generic functions on this diagnosis thing. For instance, we can write try nested, or we can write try first. Does try need to be? No, I think try needs to be in this. It has to be part of the monad diagnosis. Try will be something that, given a m of a, will give me a m of maybe a, as in if that computation fail, recover and give me a maybe value. So, in our case here, try of some computation in this diagnosis thing. So I have this thing here. I'm just going to call it D. Is going to be a diagnosis T thing that, given some state 0, I will do a run diagnosis of D, and I will apply the state 0 to it, which will give me state 1 and maybe the value. And the result of this will be state 1 and just the maybe value. So now the operation has succeeded. We have a value we can deal with. And if there was no value, this contains nothing. And if there was something, this contains just the value. We've made it into a maybe value. Of course, we can simplify this because this is just an F map to of, well, it's not even that, it's just an F map. It's just a regular F map of just on this. And we can replace this thing that takes state 0 and give it to be instead, this is fmap just of run diagnosis D. There we go. So with try, we now have a thing that is able to say, well, we give it a computation, and if it failed, recover. And I think the last thing that we need is ensure. Because if we have ensure, we can take something that contains a maybe A and put it in the monad as an MA. If that value is there, the computation succeeds with the A value. If it's not there, the computation fails. So ensure will be given some maybe A. Yeah, let's write it manually. We have a diagnosis T that gets some state as an argument. And here in this case, it will be returning the state unchanged and put that MA in the MBA, in the maybe A here, which we can rewrite as being just this. However, I have forgotten a few things. Now that it is a transformer on top of another monad, now this is pure just of the thing, because we need to put it in the top monad. This is pure nothing, and this is pure MA. There we go. Now we have try and ensure. We can write the functions we've been making use of earlier today. Try nested. A try nested is going to be given something, given any monad that happen to be a monad diagnosis, I have a value that is of type M of f of A, where f is a functor. This will give me instead a well, no, that's not true. This is not true. It will, this is going to be an M of A. It's going to give me a compose of M maybe of A. And try nested is going to be simply, we run try on the computation. So we transform this MA into a M of maybe A, because that's what try does. And then we do compose on it. So this is compose dot try. And we can do the ensure nested that we have written so far as there's no functor f. This is purely on monad diagnosis. Ensure nested that given some for a given monad diagnosis M, and for as an argument, a compose M maybe of A will give me an MA. An ensure nested will be a get compose that gives me a M maybe of A that I bind into an ensure. Okay, there we go. That was some amount of work, but now all of the things we have done, if I go back to validation, let's say, where can I show an example where this would work? Maybe not here, maybe in exp. That would maybe make more sense. If I go back to yes, there we go. Here, this thing, now, it uses the ensure nested, try nested kind of thing. I am within a monad that happens to be a monad diagnosis. So it has report error, report warning, try and ensure, and therefore it has access to the try nested and ensure nested functions. This try nested will take this thing. Report doesn't exist yet, but bear with me. That will use the report error thing that we have written. So this whole thing in our diagnosis monad the value will be a nothing. So it will start short circuiting from there. There will no longer be values to apply. This try nested will convert it into a compose of our monad and maybe. And here at the top, we will do an ensure. So the try will make it into a maybe value. So we will recover. So we will continue iterating on the fields. And at the end here, this ensure nested will convert back into a maybe and go back to a nothing at the top if the execution failed. All of this because we've put deriving monad here, basically. Okay, and I think that's basically all we need for diagnosis. Well, no, that's not all we need. We are gonna need the big thing of monad yeah, at this point, I'm no longer in the talking about monads thing because this is getting a lot more complicated. This is what we call, again, a monad transformer, when I can stack some monads on top of another. For instance, here, my validation monad. It is a monad that is a reader of the validate info on top of a state of the validate context, thing I've been using throughout this project. The M that is underneath here will probably be our diagnosis monad. And under diagnosis will probably be IO or something like this. The thing is, I want to be able to use those, where are they? Report warning, report error, try, and so on. I want to be able to use them at the level of, if I'm stacking things on top of one another, I want to be able to use them in my validation monad. So that means I need to make my validation monad an instance of this monad diagnosis thing. So I need to implement this type class for my validation, which is kind of a lot of work. And I don't actually need to do that. Oops. No, I didn't lose anything. Because I can make this thing, it is already, thanks to just being reader T, it is already an instance of monad trans, which is a funny name, that allows it to say basically, oh, it is a monad based on top of another. Here, for instance, I don't know if I can derive monad trans. Probably, since it's a new type. But I'm going to write it for myself just at first. Diagnosis T is an instance of monad trans because it provides lift, and the type of lift is function from some value A in M into a value in diagnosis T of M of A. So from the monad underneath to the monad on top. And lift of X will be a very simple diagnosis. I really can't type, I'm sorry. T of given some state, return the state, and put just inside the X, which we can rewrite as being that. But again, I am fairly convinced, since this is a new type, that I can write it like this. Another thing I might... I'll do that if I need it. I don't want to add more stuff there. And I think what I want to write as a result with this class monad diagnosis is, I think this will work. If I have a monad diagnosis, if I have some type M that happens to be a monad diagnosis, and I have, oh, is Twitch still? Apparently Twitch was not working very well, and I hope I didn't miss any of the chat. I am not familiar enough with Elixir, so I cannot answer that question that I just saw, and I don't know how long ago it was. Sorry about that. I think apply is a lot more about... Yeah, I think it applies a lot more about what we call in the same realm as curryfication of like applying arguments to functions more than it is about the kind of like nested kind of thing, I think, at a look. But again, I'm not familiar enough with Elixir. I'm not gonna make guesses. But yeah, I think this will work would be okay, if I have okay, that's good. At least if the trim is up, that's the most important part. If I have some monad M that happens to be a monad diagnosis, and I have a monad that happens to be a monad trans, I should be able to say that this that M of T, sorry, T of M is an instance of monad diagnosis. So anything stacked on top of something that is a monad diagnosis will be a monad diagnosis. And this will be true. Yeah, okay, I'm not sure enough about Elixir. Again, I'm not going to risk saying something completely wrong on stream, recorded for eternity. And the idea here is we have to implement those things. Yeah, I think it's just like, okay, this is closer to what we call curry and uncurry in Haskell, I think. Because the idea of Haskell, you've seen like the function type that looks like this, where like a function of two arguments, like takes two int, for instance, will be int, arrow, int, arrow, int. And that's because all functions are curried by default. So if I have a function foo like this, if I do something like bar equals foo of 4, despite the fact that foo takes two arguments, that's perfectly valid, because a function of two arguments is something that takes one argument and returns a function from the second argument to the thing. So if I do foo of 4, I only give one argument there. The type of bar is, well, we've already given this int, so what's the result of this int? Well, it's that. So the type of bar is function from int to int. And now I can do bar of 5, and that gives me, well, an int. That's called curryfication of functions. And so you can apply the arguments one by one, in a sense. And applying an argument gives you a function from the next argument to a function from the third argument to, and so on. And we have two base functions in the language, curry and uncurry, that convert back and forth, basically. Curry is, I have a function that takes a tuple A and B, giving me a C. I make it into a function that takes A, returns a function that takes a B, that then returns a C. And I have uncurry. Oops, I swear I can type. That is the opposite. I have this A, B, C thing. Like A takes A, returns a function from B to C, and transforms it into a function that takes a tuple and returns the value. Yeah, the way I remember them is like, currying is the thing where I can give one argument at a type. So if I have something that takes a tuple, I cannot, therefore I need to curry it to be able to do that. Uncurry is going back to big quote normal, therefore it's the one that gives me back a function from tuple. But I rarely use them directly. The most common use case of them is just like, oh, I zip with something and I have a tuple and I need to apply a function that takes two arguments to that tuple. But with zip with, usually you can avoid that step. So I rarely use curry and uncurry manually. What did I want to add here? Because I think, oh, yes. Yes, I was removing this. The last thing I needed here was I need to write report warning, report error, try and ensure. Nope. So curry, if you look at the types, curry is this, and fmap2 doesn't exist. I need to define it. It is fmap.fmap. It looks like this. So curry fmap is, I apply a transformation function nested within some structure. Look, here I have some f1 of f2 of A, and I create an f1 of f2 of B. So if you were to see it if you were to see it in a slightly different way of transforming functions, fmap transform a function from A to B into a function from FA to FB. And curry, well, uncurry in this case, curry would be, I'm going to say C here just for clarity, transform a function from A and B to C into, I'm going to try to align them for readability, into a function from A and B to C. So it's about changing the shape of the function rather than nesting the function. So here what I want to do is I want to do this, which is basically, okay, I have some monad M on which this has been implemented. So I have report warning, I have report error, I have try and ensure. Probably that monad is diagnosis T itself. And now I have, well, I have another monad stacked on top of it. And I want to say, well, if the thing under can do report warning, then this one can do report warning as well, right? So let's write this. We know we have the lift thing. So if I report some warning W, if I use the report warning of the underlying monad M, I get a value in that M itself. How do I get a value from here to the thing on top? Lift. So this is lift report warning. Report error is similarly lift report error. Try is going to be a bit different, I think. Is it not? Haskell docs are often pretty decent. Which ones have you found that are broken? I'm curious. Try is going to be the same. No, try is going to be more complicated. Oh, for base. Base should be correct. What's broken about them? That looks correct to me. There are some backquotes that are wrong in the only the last type parameter can be modified with fmap, but otherwise that looks correct to me. If you bifunctor, the link is broken. Interesting. Let's see. Is it trying to go? Yeah, okay, because I think bifunctor has been removed from base. I don't remember. Oh, because no, there it is in base. Where is that link going that's broken? Oh, because it used to be in something else. Oh no, I think the link is actually broken, you're right. Let's see, this is the base for 4.21. Let's see if for a more recent version of base, I'm going to do it on this computer so you can see what I'm doing. No, so I want that, and I want to, the one that's broken is for version 4. That's the most recent version. That's fun. Okay. And that's in which one is broken again? In the prelude itself. Okay. Yeah, it tries to go to data bifunctor, and I think that's yeah, that's broken. Let's see the source. Oh, actually, let me put the chat back. There we go. Where is bifunctor in this? Ah, yeah. I think it's that syntax is wrong. That's fun. Oh, is it because here the type is explicit? Yeah, I'm not sure. I'll try to see if I can fix that and maybe open a pull request. That'd be fun. But here we have a problem. We have a problem, which is that I'm not sure how to do this actually. Rather, I'm not sure there is a solution that works for. I don't think I can write a generic solution for any monad trans without using some. I'm not a maintainer, but I could open a pull request, I suppose, or like go on the. Since this is part of base, it will be part of the GHC code base, and I could open a pull request for this. I have submitted one PR to GHC a long time ago, so I've done it once. I guess I could do that, but I'm not a maintainer. Now the problem here is I don't know how to write try in a way. I cannot write try in this way because I cannot just lift because the type of the M here will be of the transformed monad, so this won't work. Is it time to lose all of you and even myself and look at monad base control? It could be. It could be. Let's have a look at monad base control. Well, not monad base. That's not what I want. Monad control. There we go. That's fun. If you don't mind sending them to, like, if you find a list, send them to me on like Discord or on Blue Sky or something like this. I'll try to see if I can fix them. That'd be fun. Yeah, I think this is what I want to do. But I've never really bothered to do things with monad-based control. So will I be able to do that? What is run in this context? It is okay. Yeah, the thing you can do is a thing you can use is Hoogle. Hoogle is absolutely fantastic. You just search for a thing. You can search for like, oh, I want to know what a bifunctor is. and it will just like tell you what kind of things are called by functor, where they are defined. Like there's a class in this particular module. In base, that's a module called data by functor. But you can also search for like, oh, I have a function from A to B, and I have a maybe A, and I would like a maybe B. Is there a function that does that? And it will tell you fmap. And you can then go to fmap, look, see it's defined in prelude, and go look at fmap and so on. Hugel is fantastic. I cannot recommend it enough if you're looking for a type of something, or if you have a shape and you want to know there's a name for that shape. Hugel, fantastic. Okay, let me see if I understand this correctly. So I would need a monad trans control. So import monad trans control. That's okay. And what I will want to do here is I will need to rewrite this to instead be on a monad trans control. And try will be rewritten differently. Try will therefore be, I have some action, I have some MA, so I want to try that thing, and I want to then lift it with something else. And let me see if the examples make sense to me. Is it just something like lift with of run, try run action? I think it would be something like that. We'll see when I try to compile and it breaks completely. But ensure is going to be a lot easier because ensure does not require the state of the thing. Ensure is just lift of ensure. Okay, so try is going to be the difficult one. We will see if this is correct when we get to a point where we can actually compile this thing. There we go. Now, that's our diagnosis monad. Another diagnosis messages. There's one thing I'm not sure about is this thing here, but if it works, basically we have said this diagnosis T is a valid implementation of this interface type class thing. We can do report warning, report error, try, and ensure. On top of this we can write try nested, ensure nested on any monad that has this contract. And this thing here is saying, well, if it's a monad diagnosis, there is a monad diagnosis, and I have some stuff stacked on top of it, I should be able to just use report warning, report error directly. I should be able to use those things in the monad above. We are way past the realm of monad 101 at this point. Now we're gonna need something else. There's a few places in the code where we assume that this thing exists. That means, for instance, if I go back to analysis and I go to resolution and I go to monad here, this thing, I will require the things, this M, to have a monad diagnosis, but I don't want every time I need to throw an error to have to create the diagnostic from the base name, the location, and so on. I want to just be able to get the message and create that from my state here. So what I'm going to write is I'm going to write some functions for this scope. I think I've named them report and warn. I'm gonna keep this name for now. Or maybe I go back to fatal. Maybe fatal is better. Fatal is gonna take a diagnostic and return a resolve t m of a, regardless of what it is, because it's gonna just throw an error anyway. For this to be true, we need M to be a monad diagnosis. If it is, then resolve T is a monad diagnosis, and so fatal is going to be open a do block. We are now in this monad. I can get the base name by getting it from the declaration name. So the base name is view ARI declaration name. The location is use of the RC location from the current state. Those are steps in a do block. They are translated into the and then in this monad, which is this thing, which is a complicated chain of functions inside. So I can do things state by step by step, and the chaining that does all the state carrying is performed by me by the and then. And after that, what I do is I use the report error function from the monad diagnosis to create. So I have the message here. Oh, so this actually takes a message. I have the error, the diagnostic message here. And now that I have the base name and the location, I can report an error with a diagnostic that is made of the base name, the location, and my diagnostic message. And I will call the other one warn. I guess another solution would be, if this monad-based control thing doesn't really work out, trans control, I could change this to, instead of implementing it once and for all types, I change this to be like, actually, this takes the message, and I let each monad decide how this is implemented. But for try, that would, and ensure that would be a tiny bit annoying, so I don't think I want to do that. And warn is going to be the exact same thing. We get the base name, we get the location, we create the diagnostic, and but instead of report error, we do a report warning. Or do I want to rename them something different? Fatal, warn. What would be good names for those functions? Fail with, warn about. I don't know. I think fatal and warn are good enough. And I'm kind of tempted to introduce, it's fine. I was going to introduce a helper just to deduplicate those two lines, but I think it's fine. And we can do the same thing for validation now. We can say that validation t, the difference is the base name and the location will not be obtained here. I will need a context name, context location, which are used by current name, current location. Okay. So here this will be use current name, use current location. And it's going to be the same thing here. And provided that all of this works, we should be, and provided that we do the renaming properly as well, we should be done with the diagnosis monad. Which means there's a bunch of places, such as invalidation here, where we're going to need to do a replacement from monad M to monad diagnosis M, which actually I should do here. I should put the constraint here, which I think is, no, it's going to be still required here. Okay. Okay. Oh, I think my lift width is wrong. Let me just have a look at this again. Ah, no, it might actually be correct. So this function takes... No, I think that's correct. Provided that I understand how runt works, my implementation is correct. Okay. Okay. I think it has changed name. I think it was called that base control before. Oh, there we go. There it is. Oh, it was because, okay, of course, this is for the thing at the base. I'm confusing the two of them. And monad trans control is the one I want here. Okay, yeah. That's something I'm slightly less familiar with, but I think it should be correct. We will see when we get to a point where we can compile, which we're actually getting close to. I think one of the last thing that we're missing. I'm tempted to try. It's getting late, but to push a bit because we're getting close. I think tomorrow evening is the point where we've made enough progress in the refactor that we can be like, actually, no, let's compile. And see all the things that are broken. Because diagnosis has been... I think brainfuck matches what you describe. But that's cheating a tiny bit. Okay, so yeah, what are we missing? We are missing the top level analysis. This function has to be redone. It's completely wrong. But now we can also rewrite it using monad diagnosis, which is nice. Oh, I'm missing one thing in monad diagnosis that I want to do actually. I've used this run diagnosis. This will not be exported out of this module. And in fact, I'm even gonna not name it at all. Which means if it's ever used, it is used. Here, I'm gonna have to instead decompose this into the step function. And this is that. It's not used anywhere else. Okay. And the reason why is because the way I will want people to get out of the diagnosis monad will be with a different run diagnosis that will look something like this. You have a diagnosis, run diagnosis T, I suppose. You have some kind of diagnosis T value with some M underneath and some A value within. And you return M of maybe A. So if I have this action that is a diagnosis T of the step function, then what I need to do is call it on the initial state, which is the initial diagnosis state, which is gonna be a diagnosis state with an empty sequence. I can't type, I swear. And a Boolean that is false. There has never been any error. This gives me a final state and a maybe result. Now, this is where I want to be careful. I want to check that even if this thing is just a result, I don't want to return it if this thing here tells me that there was an error at any point. Because even if we recovered, as a whole, I want the computation to fail. So here in this case, this is going to be a if ds any error. Oh, in fact, no, this is wrong. I want to return the sequence of diagnostic. I want to return all of the stuff we have accumulated and the result. But if maybe I'm just gonna actually diagnosis state, I'm gonna decompose it. If any error, then what we return from this is a pure, we put something in this monad M of a tuple, which is the ds all diagnostics, and nothing. Because even if this thing succeeded, if there was any error, I don't want to return. Otherwise, what do I, and I guess I could as a result rewrite it as pure of, we return all of diagnostics and the maybe result, whatever it may be. Which I know for certain, if there is no error, will be just a value, but there's no point in trying to do anything else at this point. Okay. Okay, so now anyone who uses this function, uses this thing, if I don't export this constructor, is forced to run this by this thing, and this check will happen every time, which is my goal. And finally, I can do a run diagnosis for the non-monadic version of this, where there is no monad there, and that is just that is purely run identity of run diagnosis T. Okay. Okay, let's go back to the last thing that we're missing in the validation, and then we can try tomorrow to write the top level function that is missing, and then we can try to compile and then we can try to compile and see a month of work and see all that's broken and then fix it. A brainfuck editor would be very fun. I'm looking forward to December for the advent of code. I'll definitely try to do a bit of brainfuck there. Okay, back to expr, because I think the function call is the only thing we have left to do. So I guess the first thing we have to do, and I'm going to do it in the do block for a reason that will be clear later, I will probably want to do validate function. Well, callable object, which is going to be checking the function name thing. This is now, in this post-refactor world, it is now a role. If we go to resolved, It is one of those things. So let's have a look at which ones are valid and which ones are not. So built-in type, that would not be something that can be called like a function. Built-in function, yeah, sure, that sounds good to me. Struct, no. Enum, no. Constant, no. Function, yes. Type alias, no. Type parameter, no. Placeholder, no. A function argument, one day, but we don't have the ability to express that at the moment. So for now, no. And the let variable, in the current state of the language, yes. Oh, that is annoying. No, it's fine. I have already solved that problem elsewhere. Okay. So for now, this is gonna be unimplemented because I don't have any built-in function yet. Let's start with a function whose name is function name. What do I want to return here? What do I need to extract as part of this to check? And actually, of course, I want a catch-all thing where I will report something that is fatal, which is a error, not a function. This, actually, this function name is a path info. It's going to be the only one in scope. I'm going to do a path info here to deconstruct it. And this is the path name. No, it's the path body. I think has changed now. Has it? It hasn't. Maybe it should change. It's gonna break so many things if I do that. Gonna leave this as path name for now. I want to change it. Path base is a better name. That's gonna break so much of the code. We'll get there when we get there. Okay. So now, what do we want to do again? We want to, well, to check what the function accepts, I'm gonna need to return, not result, validated. I think I will need the function info. I will need the function info, which is not the function info, the function type info. Which is this. Where is it? It's this thing. I need to know what the type parameters are, I need to know what the arguments are, and I need to know what the type of the return of the function is. Why I didn't use a language server is the last time I tried the Haskell language server protocol thing was a few years ago now, and at the time it was a bit slow. But a bit slow I don't mind, but it would make Emacs lag. Like I type things in my editor and it makes the thing lag for a second. And lag in my editor is something I cannot accept. So I would rather work without it than to suffer any lag at all. It would not help me at the moment because since none of the project compiles at the moment, it would be broken anyway. But that's the reason why at the time I didn't use it. I know there's been a lot of work done on it in the last few years. I should probably retry at some near point in the future to see how it has evolved, to try to see if it has become a bit better. But anything that makes my editor lag is such a negative feeling that I've tried it and disabled it basically. I'm also so used of like years of working without integration like this that I'm used at this point to working without it. The upside being that I can work anywhere since I don't need any integration. Just give me an editor, I'll be fine. Yeah, I think what I need is the function type info. I think that's all I need since linking will happen later. At this point, the only thing I need is to check like, is this indeed a function? And if yes, what is the type? Is it compatible there? So that's the thing I need to get. I need to get a function type info, which is part of the type of the thing. If I have only the function name, that means that in my validation monad, there must be something that will give me the function type. And I think that will be the definition, because if I look at the definition of definition, invalidated, a function is a function type info. So what I need to do, yeah, it's possible it was something like this. I'm not sure exactly. I will need to try again. So what I will need is to go get the definition that must be in scope. As we have seen before, it's either going to be in the definitions that come from the other modules, the dependencies that we have already compiled, or the definition cache of the things in this module. So that means I am going to need oh, I already have that. Retrieve function type as traverse assert function type. That's perfect. That's exactly what I want. Why do I have this already? Probably because I anticipated that I would need this. And in expect, then I suppose assert function type. Yep, it looks for a function def case of a definition. Perfect. So retrieve function type. So here, this would just be a retrieve function type of the function name. In the case of a let variable, however, I have the identifier, and I can use that to look in my context for the type of that local variable. So this would be, do I have, yeah, I would need to use current variables. Okay. So this would be, if I go back here, I do a uses of my current variables, and the function I apply on them is a lookup of the, I probably made a helper function for this because that's an internal compiler error if it doesn't work. Did I not do that? Did I not do that? Interesting. Huh, no, I haven't. I will definitely want to do that. So let's do it here. That looks good enough. I will want to do a, or maybe not here, maybe in lookup. So maybe in context. Oh, retrieve variable type. Wait, oh, that's because this thing is written wrong. It's not VS variables. It's something that's in the stack. It's something in the context. So it is using current variables. There we go. So that's what I need. I need retrieve variable type. So I retrieve the variable type based on the identifier, and I can do a case of it to see what I have. And if the type of it is a function type with a function type info, That's great. That is what I want. Otherwise, if the type is anything else, if it's an int, if it's any other type, then fatal error not a function of this other type. You have tried to use a variable that contains an int as a function. That is not a function. Fatal. There we go. Okay. So now we can try to do attempted function info is going to be a try using our newly declared try, since this thing is going to be a monad diagnosis. Yeah, that's good. Where was I? Function call. So we can try to do a validate callable object. So if this fails, because either it was not a functional role or we found a variable that wasn't a function, like a recoverable error, this will be a maybe value. We will have recovered from the error. Why I do this is because then now we can do validated function args, which is going to be a unsure nested of traverse to of, because we're going to traverse through the list and traverse through the with location functor. And actually, no, it's just going to be a traverse because the resolve expression will be with the with location. So this is going to be validate function expression of the function arguments. Except we will want to try to validate all of them. So this is going to be a try nested of this using our try nested and sure nested kind of things. So now this will throw an error if any of those have thrown an error, but we will have tried all of them. And we will also have tried the object. So now at this point, if something has thrown an error, all of the errors will be included, and I can do a validated function info by doing an ensure of the attempted function info. There we go. Next, what can we do? Now we have the function info, so we know what type arguments it expects, number of arguments, we can do all of those checks. We are going to have to do things very similar to what we have been doing for structs. So I might copy this as a reference. Because ensure that all fields are known, this is not exactly gonna be the case here. Oh, for function calls, yeah, okay. So let's start with this. The number of arguments that are expected is a thing that is stored in our function type info, which is, again, this thing here. So it's the number of arguments, the length of the fun arguments. That's exactly what it is. That's the validated function info. The length of the validated function args is the actual thing, when expected different from actual. Fatal. Error function call wrong number of arguments. That seems good to me. This would be what do I want to put here? I probably want to put the base name of the function. That's probably what I want. Do I have the base name as part of the... No, I don't, right? It's not in the function info. No, I don't. So maybe I will want here to be function name, function info. So this would be function name, expected actual, which means we need to change this to include the base name. So here this would be, excuse me, the function name f mapped into this result. And here this would be pure. Oh, if it's a variable, I don't know. If it's a variable, I don't have the function name. So maybe indeed I want not the base name. Maybe what I want in this rare case is going to be the path base. So this. Okay. So now we know we have the same number of arguments as the ones that my function expect, which was basically what this check was about for the struct. So now here I don't have the name. Well, yeah, no, I don't have the name. So if I want to do this, I have to instead, if I do a pure on a fmap to pure on the validated function args, since this is a list of typed expression, this will become a list of type something expression, and in this case, pure will be the one for lists, so a list of one element. I can then zip that with the name of the... I can do that with the name of the argument, I suppose. Wait, check unicity. How do I do that here? Oh no, of course, yeah. Okay. The unicity is not a problem, so I don't need to do that. So the name doesn't matter. The only thing I care about is to... The only thing I care about is to establish the type of... Yeah, I want to establish the parameter map. I want to do this thing here. Yeah, everything here is just ever so slightly different. So, okay. I am going to zip. I'm going to ignore this. I have the actual expressions for the fields that have been validated, so I know they are correct at this point. And I have in my function type info, I have the list of the type of the arguments. So I will want to zip them together. Do I want to actually decompose the function type info? I might want to do that. So this is a function type info. Perfect, and perfectly aligned. That is always satisfying. So here I'm gonna zip the fun args, which is the list of the types of the arguments with the value that was given. And what do I do with them? For each of them, I'm gonna try to build a parameter map. Is that something that can fail? I suppose it can, yeah. Yeah. Yeah, if the types don't match. Yeah, I suppose. So, is it just... It's not as simple as doing a zip with, I think. It might be just as simple as doing a zip with. Let's try to do that. So this would be the parameters map. It would be a zip with build type parameter map. It will be a sequence of that. I'm sure there is a function that does sequence of a zip with. And the first argument would be the fun args, because build type parameter map takes the parametric type first. It is not in here. Where is it? It's in type, right? Yep, it takes the parameter as type, okay, and then it takes the type, which will be so I zip this with map type info of the fun args. So that's the list. No, that's incorrect. It's fun args first, and it's that on the validated function arguments. So I have here a list of the types that are expected for the arguments of the function, parameterized by the template type of the function. So if the function is parameterized by a type t and takes two value of type t, this will be a list containing t and t, basically. And here is, I have the list of values that have been given as argument to the function, and we have checked that their length is correct. So I get the type of the expressions I have given as arguments, and I zip that with the list of the expected type of the arguments. And the way I zip is by using this build type parameter map function. There's probably a zip with m, right? Go zip with m. It exists, perfect. Given a function from an a and a b and returns some c in a monad m, actually an applicative m, but that's fine. We have a list of a list of b, returns a monadic list of c. So for each of them, apply the function to like the combination of a and b, and then at the end, lift the thing back up. So here, instead of a sequence or a zip with, this is a zip with m. We apply this monadic function on all of them, build type parameter map, and except I don't want to do that. I want to do a try-nested. Oh, the Blackbird, it's back. This function takes two arguments, and I want to apply try-nested on its result. So, Blackbird. And therefore, this will be an ensure nested of this thing, where I'm zipping with this thing the expected types with the actual types. Okay. collect parameter maps. And I suppose I will probably want to then combine them into one big map. But I think that's what we do at this stage, I think. This is where I would actually... I see. This is where I'm going to need to, instead of doing one parameter map, I'm going to need to do a union with this operator for fmap. Yeah, I'm of two minds about it. Sometimes I like writing fmap explicitly. Sometimes I prefer the operator. I don't know. It is not, the logic of it isn't as bad. Dollar is function application, right? So if I have f applied to a plus b, then I can do f dollar a plus b, and that's the same. And it's not, especially in the language, this is defined in terms of the language. Dollar is just defined as being, I have a function from a to b, and I have a value of type a, and I get a value of type b. You could even implement it as being, you know, it's a function from a to b and from a function to a to b. Dollar is just ID. It doesn't do anything except creating some syntax. But you can also write it like f dollar x is f of x. That's basically the same thing. But if you see it that way, then why fmap is called the other way around kind of makes sense, in the sense of like, oh, nested dollar is a function of a to b that it is being transformed into a nested fa to fb. So dollar is that, and this one is, you know, that's the logic I see in the name of the operator. But I agree that it's not the extreme reliance on operator in the Haskell language is why I think is one of the most difficult things for beginners. I have referred quite a lot in the past about this proliferation of operators as the curse of Haskell, because you can create your own operators, and the language does. Again, dollar and this one are defined purely in terms of the language. They are not part of the compiler. And you can define whatever you want. If you ever want to define, you know, you are building a DSL and you want to define a pipe plus pipe operator, because you can, and exactly like the Blackbird is defined purely in terms of other dot operators. You can define as many operators as you want. It's great power. With great power comes great responsibility, and not all Haskell developers use the level of responsibility that would be required with the power that comes with custom operators. And that is, even though I think sometimes it's great to have the ability to do that, especially when like you are able to use things in the infix form. It's true, especially when you start doing monadic stuff for beginners, and you end up with like, I bind into a lambda that then do an f map on the thing, and it's like, oh yeah, there's like fewer letters and symbols on that line. And like someone who's experienced with Haskell has no problem reading this, but it is absolutely not trivial. And I think a big hurdle for beginners. And that's why the Blackbird is, again, explicitly by name forbidden in the Google Haskell style guide. So here, I think this is, oh no, this is required. So the only thing is this build type parameter map is gonna give me a monadic list of identifier to type. Okay. That means that here, after doing this unsure nested, I have a list of list. This thing is a list of tuple identifier thing. Okay. So unions with would be correct. Except would there probably be an M unions with, actually, but that's fine. The only thing is, I won't have the unions with is the way, like, how do I combine the different hash maps that I make out of all of those pair key values, basically? But it means that the values can be concatenated like this, which they cannot. Which means I am going to need first to make every value into a list. And that means this is where I'm going to need the fmap2 pure, or is that an fmap3? I have a list of tuple. It's an fmap3. Okay. So now I get my parameter map. This is basically going to be the same, except this is going to be the function type parameters. I don't have the function base name. That is annoying. That's fine. So here I'm going to iterate on the function type parameters, which are coming from they are just params in this case. Where do I have the struct type params? Oh, but those are the resolved ones. Okay. Do I have the resolved type arguments there? Wait, I do actually have them. I do have them. But was that correct in the context of a struct, actually? Let me check for a second. Yeah, it was correct. Okay. I'm just going to check something in the function type info. Wait, I think something is wrong in the struct thing. Something is wrong in the struct thing. I am iterating over the struct type params, and when I traverse this, base name type map, I have a tuple there, but struct type params is not a tuple. So I think what I meant to be iterating on is this thing instead. The values. Because what I was trying to do yeah, I don't care about the partial type whatsoever. Ah, no, I do actually. Ah, that's annoying. So I need something that gives me the name and the type. So I would need to do a zip of the identifier. It's just struct info. That's what I want. I want that. So I want not this. but the struct values is what I want, I think. It's those I want. Except, no, that's not correct. That's not correct at all. I need a mapping. I need a mapping from the type parameters to the values that were provided. It is that. What is that? Is something is so wrong here. Okay. Is that intended to be a zip of struct params to struct type params? That would make a lot of sense. Struct params is the list. There we go. And struct type params. Yeah, that's what it is. Okay. And that is the thing I want to be iterating upon here. Okay. So that's why this was weird. There was something wrong in the struct thing I'm using for the base here. That makes more sense. Now, I no longer have this thing anymore. Here I have a map from type parameter to the types that we have collected from the expression from the arguments. Oh, there's an error in the struct code. There is an error in the struct code. Okay, give me 1 sec. The error I have in the struct code that I need to not replicate in the function code is this. In this validate parameter function, what I do is, oh, okay, there is a type parameter to this structure. Here's the partial type I have given. I may have given the actual type, int, this structure is parameterized by int, or I might not have given it. We want to make sure that we can infer the type based on the information we have. So if none of the values of the fields give us anything about what this type is supposed to be, then this structure is ambiguous, right? And if it gives us different possible types, for instance, a structure pair of T that has two fields of type T, well, we can collect the expressions of the two fields and check that they're both the same. And if they're both the same, then we know what the type T is. And this is what we do here. We have possible types, which are the types we have found. And unless they all match, we found some incompatible types, and therefore this is wrong. But there's also here, we validated the type pattern, which is basically is the thing that we have found compatible with the pattern that was given to us in the argument. And if the pattern was placeholder, yeah, that always works. But here is the issue. If I give the argument explicitly, but then none of the fields contain the information, this list will be empty. And if this list is empty, it's fine as long as the partial type is actually concrete. So when is parameterized, not parameterized, it's partial, when has holds of the partial type, then that's a fatal error because we don't have enough information from the type pattern, and there was no field in the struct that gave us the information. Otherwise, it is not, and we can return pure param name and I guess I could try to reify. Let's go back to types. Yeah, I have a reify type here for parameterized type. I kind of want to try to do something similar for like partial types of like this would not be reify. It's kind of the same thing, but this would be more. What is a synonym for reify I could use for a function that is basically similar but with a slightly different type? Attempt to make concrete. Is there a verb for verb to make concrete? Concretize. Yeah, I suppose. Which will be here just taking a partial type and giving me instead a concrete type. Except this is going to be a maybe concrete type because we might fail. Now, what the heck is a partial type? It's this, but at any point we have everything is wrapped by a functor in which something could be maybe. Kind of the same thing that we have here. So I'm just going to do that and do that. And instead of this will be nothing, and we return nothing. All of the others are pure. Well, I guess I don't even need to do an H pure in this case. This is just an in type, just in all of those. Well, except since this is recursive, those cannot be just, they cannot be that. This would have to be oh, where's reify? Oh, they're below here. Okay. I need to copy that too. So reify struct type will have to give me a maybe thing as well. So this is going to be struct type f mapped into reify struct type. And here, same thing. Here, function type f mapped into reify function type, except not reify, concretize to be consistent. Concretizing a function type will be, since it's going to be in the maybe monad, I can just do that, where the args will be traverse with concretize function arg, the function argument. The return value will be a traverse of concretize type of the fun return, and we will be able to return. I could make it as a fmap operator thing, but I don't want to do that. This will be a function type info of the concrete args and the concrete return if and only if both of those operations succeeded and gave me a maybe. So there was never a nothing. This is never right. This is always just. Okay, this is all the same, except this is an F map. And this is concretize. And mappings doesn't exist. And for a struct type, this is going to be very similar. So I'm going to do a do block the same way. So this is going to be the concrete type parameters is going to be this. The concrete field is going to be this. Except those are now traverse and traverse 2. And this is concretize. And that doesn't take any mappings argument. If this succeeded, we can create a struct type info with the struct name, the concrete type parameters, the concrete fields, and the struct info. I don't know if the struct type info still contains the struct info. I don't think that's the case. I think that's no longer the case. Yeah, the type info doesn't contain a lot of things anymore. It doesn't contain the fields at all. So this goes away. And I suspect here as well, this is just that now. Okay, so that should be fine. So now we can go back to here. And instead of when has holes, I can do instead a case of concretize type of the partial type of nothing. Well, that failed. That means that we don't have enough information in the arguments, and there was not enough information in the type that we have given as a thing. Otherwise, we do just get a concrete type, and we can instead return a tuple of the parameter name and the concrete type. In the case where we have found some information in the possible types, wait, do I have those been reified, or are they all still parameterized types? No, by definition, I think those have to be types because they are built from the concrete types of the arguments. So all of this is concrete. So yeah, okay, we're good. Okay. So I think that hasn't changed. And we can come back here. So we have... Wait, did I modify the wrong function? Oh no, I was fixing a bug in the struct code. I was fixing a bug in the struct code. So I'm going to come back here and copy this version for the function version. There is no base name, that doesn't exist. The type map is the parameter map we have created. And we do get indeed parameter... No, we don't get the parameter name. We don't care about that. Do we get that? Could I get the name of the arguments? Would that be useful? Oh, wait, I'm wrong. This is not about the arguments. This is about the parameter types. I do get those. But likewise, like I have had in the other before, I'm going to need to create a map for this. Here, this was called, this was that. If I copy this, here. I think I don't need this. Yes, because I don't need to do set checks. So I only need this, and this will be... That's not correct. Let's go back to validated. This will be the fun parameters there with the path params, I think. Wait. It's from this struct type info, which was resolved as a list of partial types, of course. Here I haven't done that for functions. So for functions, I'm going to need to resolve the... I'm going to need to resolve... Where do I need to resolve that? Where do I have parameters that make sense? That is not at this level. It's going to be at the... Oh, wait, does the thing that I have, does the function info, type info? No, it doesn't have that. So that means I need to... God, this is tricky. I need to create it. In here. Because here I will assume that a function, to be a valid function pointer, all the types must be known, so there cannot be type parameters on a let variable, which is probably something I would need to check actually at this point. Like this probably requires, yeah, this probably requires, is it in type? Is it in expect? It's in expect. It's not. Is it in type? I'm surprised. It's in validate params count. So here in the case of a type variables, I want to validate variables, validate params count. Which takes as argument the list of identifiers first, which are coming from it's here that I need to do it then. I have the function type info validating it will need the identifier first, which comes from function type info. Those are the fun params. And the number of actual... Well, no, for a function... Well, no, that remains correct because I will probably want to alter the function info. Yeah. I can do that. I think that's fine. Okay. And the list is the path params, so that needs to be validated. There we go. Do I need to actually... I probably don't need to create the mapping from one to the other at this level. Yeah, I can do it at the top level. As a result, yeah, I think I don't need to do that. I can probably do it at the top level. Remove this thing to just be that. Oops. And here I can then traverse. I will need, okay, I have a bunch of types, which means I will need to get the partial types. That is going to be created by doing a ensure nested of a traverse validate partial type of the path parameters. And that gives me, well, try nested of that, and that gives me the validated the partial params, I suppose. And the named partial params will be a zip of the fun params and the partial params. Hello, how are you? Okay, with this, I now have. I had a bunch of names in the type argument to the function. Like I'm saying, I'm calling this foo of int, or I'm calling this foo with like vec of underscore. Like I'm calling this function foo with some type arguments. I have validated that the number of arguments is correct. And except here, this is going to be one of those where I want to validate with less or equal, because it's okay to not give all the type arguments for a function. It's okay to give 0 of them as well. Then I validate all of those things, like, oh, you're saying foo of int is int a type. You're saying foo of g is g a type in this context. We validated that. And now we have created a mapping, well, a zip, so it's just a list, but between the name of the parameters and the partial information we have about them at this stage. Then this doesn't change. We validate the number of arguments. That's very straightforward. Then we do that thing where we look at all of the arguments given to the function. We look at the concrete type that we know what each expression has because we are compiling a function, and we map that to the expected, to the parameterized type of the function argument. For instance, we are calling a generic function. We know that its first argument is of type t. Whatever t is, it's one of the type parameters, and we see that the argument we have given is of type int. We can create a mapping like, oh, t is probably an int. We can create, but maybe the first argument is a foo of t and u, which is two different things. So we start doing mappings from the letters to the actual concrete types. This is what we do here. Here we then do, okay, for a type t, what types do we have? And this is the, we might need to change a few things compared to the version we have copied. But no, I think it's all the exact same. Did we find no information in the arguments? Then we must be able to know what the concrete type is purely on the type parameter that was given. If we fail, the type is ambiguous. If we succeed, perfect. We know what type the argument is. Otherwise, if we found candidates of like, yeah, sure, based on the arguments, we can know what the type is. First, we need to make sure that they're all compatible with one another. If I have two if it's a generic function, parameterized by a type t, and I have two arguments of type t, then the type of the expressions I have given for both arguments must match. If they don't, if I have a function that is parameterized by a type t, and both arguments are of type t, and I give an int and a character, those things don't match. Because I have more than one candidate type, that's an incompatible type. We check that it also matches the type pattern. If I've said explicitly character and I've given two ints, that's also wrong. And we can return for that parameter name the actual concrete type. Then, with all of that done, this was copied from the struct validation. So it says to create a struct type info, which is incorrect here. So, wait, this is a hash map here. Is that correct to have? I'm also debugging the struct one at the same time, because here I return a thing of the parameter name and the concrete type, which gives me then this struct type params. Oh, it's a... Yeah, I don't use it for anything else. I could just return this and not bother with returning the type name. I only care about the actual type. So this becomes, since I only... I'm not in compilers... Well, I kind of was for a time. I had the job from 2020 to 2023 in which I was working in a company that was working with Haskell, and we were developing a tool that, given the shape of a database, like you have a Postgres database, or so when we extend it to other kind of databases, you describe the schema of it. We would generate a GraphQL schema from that schema, and then given an incoming GraphQL query, parse this into an AST that we would then translate into corresponding SQL requests to the backend. So basically, here's the shape of your Postgres thing, and we automatically expose a GraphQL endpoint for it, and we compile GraphQL queries into corresponding SQL statements. And that technically was not a compiler, but the logic was basically the same. Compile it into an AST, transform that AST into an IR, and then generate a corresponding, like generate statements for the backend based on what kind of database we're targeting underneath. A very, very fun project I worked on during that time was the part where we generate the schema from the database. We were doing a thing where we generate the schema and the parsers at the same time by writing a thing that like generates both, to avoid having to generate like the two of them separately and then ensure that they're correct. Like we look at the database and we say, oh, this must be exposed as an int, and the parser actually expects a float or something like this. So making the same code generate a thing, a static parser that can be introspected to extract the schema. So that's, not really a compiler, but also kind of a compiler. And I've written, the cleanest, this project is my attempt at being as clean as possible with writing a compiler and being as close as possible to a real language, while taking a lot of shortcuts for it to be done by one person on a stream that I want to be somewhat approachable. But it is definitely the one I'm putting the most effort in. I've written a few like shitty compilers in the past, but this is definitely the one, like as a personal project, that I'm putting the most effort in. So here again, we only need the concrete type. And here, as a result, since this is just, when I have the concrete type, I return this becomes, Haskell is definitely a language that makes working with that kind of stuff very easy, because working with tree-like types, working with recursion, working with that kind of stuff, the language lends itself to this pretty well. There is a part of the code I'm in the middle of a big refactor I haven't compiled in weeks, but there is a part of the code I will have to rewrite, which is the simplification phase. And it showcases how elegant the whole thing is, because this is like, a thing is simplifiable if it provides a simplify function that from itself returns a new version of itself, basically. And I have this thing where like I just, given some definitions, I simplify them. That's what this does. And this whole function is just like, yeah, how do I simplify a definition of a constant? Well, I uh, recreate a constant info by simplifying its arguments. And at the bottom of this, I have this big thing for simplifying expressions, which is a rewrite, which applies itself recursively until there's nothing that can be implied. That says the addition of a left-hand side plus 0 is just the left-hand side. Addition of 0 plus the right-hand side is just the right-hand side. And this is applied recursively until there's nothing to do, because an expression will be entirely rewritten by just using rewrite to do this case of the thing. And like this small module rewrites an entire AST by just saying simplify the things and just providing the matches of when can an expression be simplified. Like division of the left-hand side by 1 is just the left-hand side. So for like tree-like structures like this, for ASTs, for manipulating things, like Haskell is fantastic. And as a result, for compilers that are a lot about tree structure-like manipulations, yeah, Haskell is pretty good. So here this thing gives us a maybe value, and we only want to throw an error if that thing is nothing. So I can use my convenient on nothing m helper, and that becomes this. And the do block becomes unnecessary, and I can probably do uniplate. Is uniplate the thing to create plate based? I think it's included in lens, right? Or am I wrong about that? No, okay, it's not. So no, I haven't used uniplate. Let's have a look. Ah, gotcha. So it's using this. That makes sense. Because yeah, the thing as you have surmised, what I'm using is the plate one that is just the base plate of lens. No, I don't want the plated. There we go. I'm using the plated one, which is from lens, and I think uniplate is a re-implementation of that, if I understood correctly. Which is basically like it's the same example here for expression with the thing, and I think it even has like a thing called uniplate, which is why I was confused. I was thinking of this uniplate in lens rather than the uniplate package, which is something different. But yeah, it is a somewhat similar concept, and indeed, this rewrite I am using here to do the recursive rewrite is coming from the plated here. If I look at rewrite, it is given some plated value and a transformation from A to maybe A. Apply this rule everywhere you can, basically. Ensures that the rule cannot be applied anywhere in the result. It is based on this plated. So exactly similar concept as this uniplate package, as far as I can tell, because again, the name uniplate seems to be the same in here. So I'm assuming there are a few packages that try to attempt to rewrite lens, because lens is verbose. And I would suspect that uniplate is really like focusing on trying to rewrite this specific plated thing, which in fairness is very isolated in the big control lens package. Yeah, lens is something. I have a package on Hackage actually that is based on lens, that I had submitted for like maybe it is oh god. I have a package on Hackage for an extension to plated, but it was never merged in control lens. Which one is it? It's called indexed plated. Actually, it should be on Hackage. Can you? Yeah, of course. And the only difference with plated is rather than having just the self-recursive thing, you can have a user-defined index that points to like, okay, in the tree, it can be the depth, it can be whatever you want, it can be a unique identifier, which so it's basically the same functions as plated, but with this index on top of it. Well, yes, a zipper would help with this, but like all the tree manipulation in a language that has like explicit pointer manipulation um, is imperative, you can very easily like lock yourself into very verbose, very difficult things. Haskell makes that a lot easier to write usually. It is, I mean, all of those languages are Turing complete. You can write a compiler in any language you want. You could write a compiler in brainfuck if you wanted, but you know, there's degrees of comfort, and in my limited experience, Haskell makes this very easy. Well, it depends on what easy is a extremely relative thing, right? Depends on what you're used to, depends on what you're comfortable with. I find personally Haskell to be very comfortable for this. Okay, so I fixed this thing here. I'm gonna copy it for the function case because I don't need to keep track of the parameter type name. The type is all I care about. Excuse me. So here at the end, here is the type parameters that we have solved after we're done. So we have validated everything. We know that the number of arguments is correct. We have validated that their expressions are correct. Have I actually done that at this point? Yes, I have validated them with function expressions, so that's done. So the arguments have been checked. The types have been resolved. We have everything. The only thing we need to do at this point is decide what we need to store as part of our result and what we need to emit as an expression for the validated version. So I think I'm just going to do that and open validated here. The expression that we're going to emit is going to be a function call. It's a call expression. We're going to need a name. I might not have the name is the thing. That is a problem. So maybe what this means is, in fact, I might need to change the way the function is written, because there are two cases for a function, right? That's why I have like validated callable object. Either I am pointing to an actual function, whether it's a built-in or a function, like I'm calling foo of something, or I am pointing to a local variable that contains a pointer to a function. When it comes to linking time, I don't have to link the thing where I don't have to do the linking in the place where the function call is made. If I'm calling something that was in a variable, I will do the linking where the variable is created instead. So that means that in a call expression, I think I have to distinguish in my result AST before the lowering into AR if I have a function call expression in which the name is known, or if I have a variable call expression where I'm calling something from a variable. And in which case, I will have not a unique name to link against, but the identifier of the variable to be used. Yep, I think that's what's required. I need to split them into two. But since the logic of all the type resolution is the same, I think I think what I'm going to do is I'm going to have this thing give me I'm going to use an either, I think. So left is going to, right is going to be the function name. And in this case, it's going to be pure of left of the identifier and of the info. I'm going to use an either to decorate the thing. Left is a identifier for a variable call expression. Right is a base name that will be translated into a name for the function call expression. Okay. That means that here, this is instead a how do I call this? This is the way to identify the function based on what kind of function we're calling. So function reference? Is that a good name? It's not a great name. Good enough for now, I suppose. Because here at the end, when I've done everything, I will need to create, in both cases, I will need a function type info, but I already have that. That's the function type info here. I'm just gonna up name. And I will need the typed expressions that are the arguments that have already been validated, and those are the validated function args. Okay. So, here I suppose at the end, the last thing I'll have to do will be a case of the function reference. And if it's left of just a var identifier, then what we will return is a typed expression, the type of which is function type. And if I'm not mistaken, function type takes just a function type info as well. Perfect. So that is the func type info. And the expression within this will be a variable call expression where we're calling this var identifier. There's no need to do any linking. We are purely referencing this variable in the function call. And the arguments are the validated function arguments. However, in the case where we have a actual function base name, then we are going to need to do something very similar. We're going to be returning this, basically. But, yeah, I think I'm actually going to do the pure here because I'm going to need to do more things in this case. The result will be of a similar shape. This will be a variable, a function call expression, where we're calling the actual name that we don't have yet, the function name, with the validated function arguments. So we are going to need to create the actual real function name being this unique identifier across the entire program that we are using in the linker. Like, it's a symbol name, basically. We need to create that, and that is created from the function base name. And it is created from map assert type, I think. Types, not assert type, that's not correct. It's called something else. How is it called again? Assert name. There we go. Oh, type no longer exists. Those are concrete type to differentiate them from partial types and parameterized types. So go back to here, and this is above. Yeah, there we go. It's here. Map assert name of the function type parameters. That gives me the name of the type parameters, the base name, and I obtained a unique symbol name for this function for the purpose of linking it at link time. And now this function name is here. The only other thing I need to do, however, is I need to perhaps register this for instantiation. I am using a very similar logic to C++ for the way generic functions are handled. So if a module A defines a generic function but never instantiates it, the symbol map of that module will not contain that function because we can't instantiate generic functions. And if B instantiates that function with int, like foo of int, for instance, then B will need to contain in its own symbol map a copy of the compiled version, of the symbol foo of int, where I am using some I'm using some cache. So if I have then C that depends from B that depends from A, and C also instantiates the same function with int, I'll copy the symbol from the one I have compiled in B already. But I need to include the symbol for instantiated generic functions in the symbol map for that compilation unit. Because, I can't always necessarily depend on the fact that, the dependencies will have it. Although I guess I could probably do in this case because I have constraints that are different than C++. But I need to, at the very least, check that it has been instantiated. Because, I'm going to link against foo of int. If foo of int has not been instantiated, I cannot link against it at a later stage. So here, whenever I encounter a base name, and I need to check function expressions after this, I need to register it for instantiation when we're done with this current batch of functions. And that will be done by looking at the validation module to see what I've done and copying it. Because when I look at top level functions, I can do this unless is a generic thing that I have here. So here this would be only when it is generic. So unless null of the fun params, I suppose, I want to check against. Yeah, fun params is fine. Am I in the wrong place? No, okay. So if the number of type parameters is null, that function is not generic, and therefore I don't need, it has already been instantiated, it's fine. I don't need to register it for instantiation. I could change the way that this is done, and always register something, even if it's not generic, when it's called. That way I won't instantiate things that are never called. Nah, I think it's fine. Okay, so unless the parameters are null and it's not a generic function, this is a call site for an instantiated version of a generic function. We must register it. And we do that by creating a request and putting the request in our instances, in our request in the state. This base name is the function base name that we have here. The definition, do we have the definition in scope? We should have the definition in scope. we might not have the definition in scope. We don't have the definition in scope. We're going to need to recover it. Okay, so we need to recover the function definition. We don't have that. The validated function type info, we already have that. This is called the func type info in this context. And the parameters are the types that we are just given. So this is the function type params. So we are only missing the definition. The definition is not the validated definition has to be checked. It's the original resolved one post name resolving that contains the actual code that we're going to need to instantiate. And that will be obtained with not retrieve definition. It gives me the validated definition. I want the function definition, which is slightly different. Wait, how does it work? Is that correct? Is that correct? Assert function definition in expect. No, that's not correct. That is absolutely not correct. This is extremely wrong. Okay. I must have been very tired when I wrote this. Yeah, none of this is correct. Yeah, because here I want a resolved function info, which is not the same thing. This is not something that retrieve definition here can handle. So yeah, this function is completely wrong. Let's rewrite it. This will be instead looking into the definitions. I suppose it could be either in the local definitions. No, it's in the local, yeah. Aha. This is incorrect. Oh, wait, no. It's the function cache. It's that. That's why this is here. I think. And I don't think the function cache is required here at all. The function cache, if I look at my interface module, is a cache for a base name of the actual definition of the function, the resolved version, not the validated one. And I don't think I need a function cache in my state at all. And I'm ready to bet that a git grep of vs function, yeah, never used. This is not required. I will need to, I haven't done that actually. I'm going to do that soon. So this is what the function cache is about. The only thing is, no, this cannot be, I was going to say, this cannot be a local function. Those have already been instantiated. No, it can absolutely be a local function. It's perfectly fine for a function A to be calling, aha. Aha. So no, I have to go back on this. I need the function cache for the local functions as well. Okay, so let's fix this. In which order do I want to do that? I want to first do the lookup function, I think. So I can finish the expression function, and then I can go fix the function analysis at the top level, and then I can do, okay. So first, let's go to context. Here, I want to fix this function. I'm going to copy the retrieve definition because it's mostly correct. Except this is going to be a lookup remote function definition, a lookup local function definition. And if neither works, this Except in this case here, this should probably be... If neither works, this is not a problem of an error has surfaced because something was wrong. It means neither cache contained the function, which is impossible if there's no bug in our compiler. So I think this will be a report internal compiler error, basically. That will be an internal compiler error with a message and a stack trace and everything. And we just need to define what it means to do a lookup in a remote function definition. And that is, I probably don't need to give those arguments because that's just a function argument that's in scope anyway. This is simply, and I'm going to copy the thing I already have here. Where are you? There we go. That's basically, yeah, those are correct. I'm just going to copy them. And there we go. Except this is the function cache, which is called functions. That's convenient. And I do a lookup of the base name and lookup local function definition is, wait, are those? No, okay, I'm good. And this is doing a lookup in the local ones. If any of those returns a non-maybe thing, then that's what this thing returns with the asum m here. And if neither of them actually return a thing, we'll try to do this, and this will be a report ice. It will not be executed unless we try to execute it because laziness. And we ensure the result. So we guarantee that we have a non-maybe, that we have an actual value in the result, and that any error is thrown back up. In this case, there's probably no need to do this. I can probably just inline them. That being said, I like having an explicit name for what each step does. I think this is fine. And if I want to be consistent, then I will probably name this as well. Okay. So that's retrieved function definition fixed after not getting it right, which means we can go back here. Here in this context of we have a generic function that we have called and therefore we have instantiated. I need to get its definition by doing a retrieve function definition based on the function base name. And I can craft this request and put it in my state. And then my name is this, and I can finally return a typed expression of type function type, and this is the function. No, that's wrong. That is wrong. That is wrong. The type of this expression will be the type of the return type of the function. This is wrong. Okay. So that means there's one more thing we need to do. Validated return type will be, so I have in my validated, where are you? In my function type info here, I have a type for the return type. Oh. No, I don't have value. I can't include this. My type inference is not sophisticated enough that I can make use of this. So I'm not going to use it for the type inference. I don't have to change the code for that so far. But I do have this fun return thing in scope that needs to be validated. And that needs to be reified at the end when I have the mappings. So when I have all the parameter maps at the end, I know exactly how each... Wait. Aha. No, here I'm going to have to do the thing I removed earlier because it's not needed for structs. Here for the case of a parameter, here I am actually going to return... It's annoying. No, I'm going to keep this. I'm just going to do a... I'm going to put this back into this to put the parameter name so that here after this, I have the list of the type parameters. And then I can do the type parameters there, which is just the second part of the tuple of this validated type list. And I can do a don't I need to reify anything as part of this? No, I don't do any reification there at all. Not as part of this. I do it here, where this is the yeah, this is exactly what I need to do here. Okay, perfect. So go back to, let's go back to here. Here at the end of this, I need to do a validated return type, which is gonna be a refi type, which takes as first argument a mapping, which is a map from list, a hash map from list of our validated type list. And the type that we reify is the function return type, because it is parameterized. If it is a function that has a type, a t type argument, and it returns a t, I need to translate that into whatever that means. Now that we have done the job of figuring out what that type t is in the context, so now I need the validated return type. And reifying types is not something... Is it monadic? I don't remember. Types. It is not, because the only kind of errors that can happen at this point are internal compiler errors. Okay. And so here, this is all correct. The only difference is the type of what we read, the type of the typed annotation of this is the return type. It is the validated return type, so that the parent can know what the result of this expression, this function call expression, will return, and can use that for further type checking. Okay. Now, we need a few things. We need to check that we do this request thing on instantiation in the other place when function instantiation can happen, and that's when an expression in a function evaluates to a function, which is only allowed for let bindings at the moment. Like, it is possible to let foo equals bar where bar is a function. We allow this kind of very limited function pointer abilities at the moment. We need to make sure that in those cases, we do this kind of request as well. So let's go back to validate function path expression is exactly what we want. Validate function path expression. Where is that used? Yeah, there we go, so one. So I found a path expression in one of my expressions. It's perfectly fine. A function is a possibility. Validate function path. There we go. This is not indented correctly, but this is otherwise correct. There we go. Unless the list of parameters is null and it's not a generic function that requires instantiation, we get the definition and we do the exact same definition. And we do the exact same thing. I hope that this will be correct. We'll have to check. Okay, perfect. With all of that done, is that all of it? Are we at the point where we have ported all of the code? Not yet. We're getting close, I think. Okay, there's a few things that are missing. First, I'm going to go over the validate function expression again. Make sure that we cover all of them. Field access, we're done. Array index non-implemented, that's fine. Struct, we're done. Literals, we're done. Strings, not done yet. There's a few places where we use report still. That's going to be changed to fatal. References. Oh, wait, this is... Oh, yeah, references. I think I want to change this. Yeah. Aha, that's something we need to fix in the function call. Okay. We need, because references are very weird since they are very limited in the syntax, we are going to want to only check them. Let me think for a second. The reason I don't want to handle them here is since they're not reflected at the type level, that means they would be valid in a bunch of places I don't want them to be valid, which means since the only place where they are valid is in a function call expression, I think here this is going to be validate function argument, and that's going to be a different kind of beast. And validating a function call argument. Oh, that's, yes, okay, that's a mistake I'm making everywhere. Okay, because when I get the type of the things and I do the type checking, I am just assuming that that the type of the arguments is just that, but it's not, because function types are not just, they are slightly different. They are weird. Okay. Where do I zip anything with them? Params, that's different. Args. Okay. So here is the only place where I actually use them. And the rest is just okay. So let me go to validated first to quickly check. Yeah, okay, they need to be expressions. The type is lost at this level. Okay, okay. So that means that I think the validate function argument must give me a typed thing with the reference information removed, but this is where I validate the reference thing, I think. Okay. So, and then if I do that, I think everything else will work. Almost, except for build type parameter map. This is not going to be correct. Because those arguments are not a list of types. I'm going to need to extract the list of types from this. The fun args are coming from the function type info. Do they? Yes, they do. And those are function arg types. So I will need to get the actual type. So I will need a function from like function arg inner type that to a function arg type of f associates a type tree of f. I should actually perhaps make plated on my type trees, but that's hasn't been useful yet. And that's a simple case of its by value of t. It's t if it's by reference of t, it's t. Okay? Which means here, this is a map function arg inner type of the fun args. Okay. And I need the validated function args to give me the right thing. So validate function argument needs to do the right thing. So do I have the function arguments in scope? They are the function args. Perfect. So this is going to be aha, but I cannot validate them in isolation. I will need to validate them by validate them against the type. So this is going to be something like I will have the function, the arg type, and the arg expression. That means that this must come first, I think. Which means it cannot use validated function args, it has to use the function args. Because then I can do this. Which means here I don't need to do this try and dance. This is just validate call object, and if it fails, and that's fine. Okay, so that's going to be basically that. Except here, this will be zipped. This will be again a zip with m of try nested of validate function arguments using the blackbird there again. And I'm going to use the fun args. This is the function, and those are the things I am zipping together. There we go. And here, validate function call argument, let's be consistent, has access to the archetype and the expression. So here is where I want to validate references, basically. And that means I have to do a case of the archetype, and if it's by value and it has a type T, then I don't care about the type at this stage. Do I? No, I do care about the type. I just realized I've never actually validated. No, I do validate that the types match when I generate the parameters map. So no, here at this point, I don't care at all. The only thing I need to do is to validate a function expression of the arg expression. That's all. I don't care about this. By reference, however, I don't care about the type here either. I need to check that the arg expression is a reference expression. And with a sub-expression within. And here, this will be a validate function expression of the sub-expression. Because this is purely a syntax thing. I'm not creating a value of a different type, so this is why it needs to be checked here. And if it's anything else, I will have to report a fatal error of error. And do I have any error message? Error function called arg expecting reference. Yeah, I think value is never used anymore. Remember this. I don't have the name of the argument here. Do I need the name of the argument? I am iterating on the fun args, which are coming from... Yeah, I don't have their name. Do I want their name? Yeah, I think I want the name just for error messages. So I need the identifier here, which means the function resolving things I need to change to include that. Which means here when I'm joining the fun args, here I have arg name arg type, and here if this is this, I can give the arg name, but that means that here function arg in a type that becomes that on the second thing of the fun args, and since I'm using this operator, let's be symmetric and use it everywhere. Okay, that should be fine. Let's look at all the places where I use the fun args. So there's going to be the same thing here, and I'm actually going to write it as an fmap of this. Length is fine, and then we're at the thing I was doing, so we're good. This is the old code that is no longer relevant. I am going to remove it entirely. Okay, we're good with the fun args. And now the last thing here is to go back to the top level. Well, last thing for now. And here in the function type info, that's wrong. That's completely wrong. Okay. Function type info has three things. It has the parameters. Oh, I suppose, yes, it's missing here. I've added the identifiers that are coming from the... Okay, so it's coming from the function definition. So it's coming from common. What's a fun type info at this level? it is the fun params. So this is going to be a lift A2 still, but the function that I'm lifting is this with the fun params and ensure, perfect, and validated function arg needs to wait. The fun args are not. Yeah, it does contain the identifier. Okay. Oh, I can do the I can at least do a try nested here. Okay, and so a function arg here will be something that contains the arg name and the arg type, and I do a case of the arg type of, and I return arg name as a tuple. Well, I suppose I don't care about the, no, I guess I don't care about that at all. I can instead do one more layer of traverse and do this as a case on the type, and this validate function arg is applied as a traverse. It's already, I was already doing that, perfect. So I was already doing that, I was already applying the traverse nested to the function archetype. So this already contained the identifier. So when I was giving that here, I was already giving a list that had the identifier. So in fact, I was already giving this shape. Okay, perfect. And with that, I think we're done for this part of the code. We're very close to getting to a point where we can try to compile. It's getting late. Oh, it's getting a lot later than I thought it would be. I might wait until tomorrow's stream to actually try that. There is a small thing that I know is missing, but I think otherwise we have done everything. That is in here. I haven't done. Yeah, there's one thing I need to rewrite tomorrow, which is the top level. We're gonna need to rewrite this function basically, and how the compiler chain works together. Now that we have like stuff for everything, and we have things to change the thing, I'm gonna do one last thing and then I'll stop for the evening, and that is I have not introduced, and yeah, I can do it here. How do we run? How do we unstack the run validate t thing at the end? Because we are gonna need a bunch of things to do that. Do I want to just take a validate info? I think I might want to do that. Like, yep, you give me a full validate info. That's your responsibility as the caller to provide me with the module name, the definition cache, the function cache, the symbol cache, all of those things. And after this, you give me a validate tm of some kind of a value. And my role is, as this function, is to run all of the things, run the reader, run the state, run the everything. And if all of that work, I should be giving you in M just the A value, because no, actually the state is required. I need to give you the final validate state and the A value in question. Run validate T will be given some info and given some action, is going to be running the action and doing a run reader T to unpack this thing using the info, and flip, and I never remember which one it is. Let's have a look at state. Is it just run state? It is run state, but run state gives them in the wrong order. So flip run state t using the initial state, which hasn't been defined, and fmap flip, not flip, swap. God damn it. Huh. Yeah, swap. Although I guess I could decide to just be okay with the way it's represented and do it the other way around, but I think I prefer having the state there, because then I have a functor of the value there, which I think is better. Okay, so the only thing left to do is to define what does the initial state look like. That's a validate state in which the definitions, there is none yet. That's an empty cache. I'm actually going to name them. The definition is an empty cache. We haven't defined anything yet. The functions are an empty cache. We haven't defined anything yet. The instance requests are an empty sequence. We haven't requested anything yet. The context is crucially empty at first. We have not validated anything yet. This is an empty set, and we have no stack to speak of yet. This is an empty insertion order set as well, which means, yeah, this is why we don't need as an argument. It is trivially constructed as just being the MMT. Most of those have a monoid instance, so I could probably, I'm not sure about the insertion order hash set. I don't know if it has a monoid instance. If it has, I could derive a monoid instance on this and just use the monoid instance. But since I have zero use for it, and yes, I missed an equal. Thank you. And with that, run validated is there. Do I have a run for the other monad here? Run resolve t is there. In this case, however, we don't keep the state. Oh, here I'm giving all the top level information separately, I suppose. I guess I could do the same thing for, let me see. Is there anything where the reader can be constructed from a smaller? Nah, here I need all of the stuff. I can't just like take fewer arguments and reconstruct this from fewer arguments. No, offset is not a typo. This is a ordered set, which is a set that remembers the insertion order of the elements, which means I can do lookups of like, is the thing in the set very efficiently rather than doing a linear lookup on a list. But if I generate a list, it will give me the list in the order in which the things were added. I'm using this to keep track of circular definitions, because I have a thing where I'm able to do, oh, I'm doing the analysis of this thing, but to finish it, I need to know what this other thing is. And therefore, I stack another validation on top of the current one. And then when it's done, I pop the stack and I resume where I was. But I use this thing to keep track of like, what is the things we have seen in this stack? It's my ordered set. So whenever I try to add something on the stack, I check in the set, is it already in the stack, without doing a linear search in the stack. Although I could do a linear search, it's never going to be very, very slow. But, you know, it's slightly better to do it that way. And if it is, then I can report a cyclic definition, regardless of how complicated it is. The places where this can show up would be things like you have a type alias A that depends on the type alias B that depends back on the type alias A, something like that. We're like, oh, to know what type alias A expands to, I need to know what type B expands to. And the type alias B depends on type alias A. I need to know what type alias expands to. Infinite recursion, cyclic definition. We block that. We avoid stacking infinitely. And the other one is constants. I have a constant A whose value I need to know at compile time. That depends on the constant B whose value I need to know at compile time, who depends back on the constant A whose value and so on. This is why I have this complicated logic here. There is a slight redundancy that I don't like, but that's okay, which is my context is this stack here, which is the validate context that contains everything about what validation am I doing at the moment. And the set here, the ordered set, is a duplicate of some of the context information to avoid having to search linearly through the stack, basically. Because the context contain what is the name of the thing I'm currently validating, the constant, the type name, the function, the whatever. What is the current location? What is the location where I am right now? And this changes as I'm going through a function. The type, this is only for function types. Wait, have I done this? Have I done this? Yes, I have. Perfect. This is only used for function types of like, oh, I need to check, I have a return statement. I need to check that the type that it returns is consistent with the type of the function. So that's also something I carry around with me rather than like passing that down. And those are like the parameters of the thing I'm currently looking into and the variables. So a lot of those are function related, but not always. Okay, so tomorrow, if I stream tomorrow, but it's a normal Tuesday, I should, unless something comes up, we should be at a point where we can put everything together. And that means that tomorrow we rewrite this function that, given some caches, and I will probably introduce another monad like I have for diagnosis, which will be my compiler monad, basically, which has like the ability to report compilation errors and contains a dependency cache. Basically, it contains all of those things as some shared state. Excuse me. Well, hopefully tomorrow I can hit compile for the first time in a week, in more than a week, and we can see what's broken. And yeah, I think I'll change this to be some kind of like compiler monad, and we'll have to rewrite this to, instead of being just run the analysis on the thing, this will be on a given module, run the name resolving phase on all of the things, collect the errors. Then if that succeeded, we can run the validation on all of this. And if this has succeeded, we can create the interface for the module, which is basically like a more complicated version of what we are already doing here. But some things are going to be easier, including the fact that we will have the diagnostic monad. We will not need to do the chaining ourselves. Yeah, we're getting close to this big refactor being done. It's going to be, I think tomorrow we're going to spend the evening just fixing compilation errors. Because if I try to compile now, it's going to be... I mentioned earlier, I used to have... Oh God, everything is broken. Oh, wait, no, is it because I did a hlint last time? No, it's a build. Interesting. That's a trivial one. I can fix it already. I used to have a job in which I was doing in Haskell something very close to a compiler. I was working on a project in which we had a thing that would translate a database into a GraphQL API. And so basically, you have your Postgres database kind of thing, and we look at the tables, we look at the columns, we look at the schema of the database, and we create something that one can be introspected to expose a GraphQL schema, but also passes an incoming request translates the AST, then translates that into an IR, and then generates backend Postgres statements. And that was extremely close to a compiler in the way they were structured, despite not being. It was more of a transpiler than a compiler. And for this project, that is the most serious compiler I've worked on, in a sense of like I want to make it as close to a real thing as possible. So I'm using the real tools that would be used. I'm using yep, I have it in my I didn't define it like this. Yeah, I mentioned that earlier. This is indeed this. But I prefer this definition, which is more readable for someone who's not familiar with this. And yeah, I'm taking this as seriously as possible because I want this project to be, if possible, a reference. So I am using Alex and Happy that GHC uses for its own compiler. Like I'm trying to be as close as the architecture of a real compiler as I can. And this is a Traverse 3. And empty. This is for asum m, which is here, and I think that's just an empty list in this case. No, happy is LR parsing. I think it's an LALR, if I remember correctly. It is a parser generator, yeah. And if I remember correctly, those are LR or LALR in this case, I think. Is it in scope? Nope. Yeah. It is LR parsing. There we go. It is LAR. And the thing is, I'm kind of tempted at some point to switch Happy, which is the one that GHC uses, for Megaparsec, which would be LL in this case, and therefore not parser generator but parser combinators, like more of an LL recursive descent kind of thing, because for arbitrary look ahead, which I might need to support the Rust syntax, I might need. There's one thing where I might need to use Megaparsec instead of Happy. Someone in a stream last week actually suggested something. I have an idea to fix the last thing that is not compatible with Rust syntax highlighters, but I will only do that when this compiles, and this will only compile next week. And this is nothing, not an empty list. Hello. Okay, so now I guess I can quickly, before I stop, do some of the fixing the compiler errors in the trivial things. This is part of the maybe helpers. Redundant constraints. Oh, I probably also don't export unions with, and I need to export it. Unions with. And what is the redundant constraint here? It doesn't need to be hashable. I suppose I don't change the keys. Okay, so now hopefully my prelude compiles. Okay, there we go. Okay, and now. Oh, yes, okay, that makes sense. This is wrong. Wait, why is. Oh, export AST, yeah. This file I probably want to comment altogether. I think I will want to change the pretty printing. I don't like the way it works at the moment. Which is gonna break all the tests, that's fine. This is common. This is passed. Because I have copied the same old file into a bunch of different files. And as a result, the module name at the top is incorrect. This one has changed names a few times. This is resolution. Name instead of verb. This is resolution as well. Here, this is my header generator that's wrong. Okay. That's good. We like to see this. Multiple declarations of validate type alias type. Oh yeah, indeed. Yes, sorry, I should have mentioned that. What I'm compiling, so this is a toy project. Again, I'm trying to take it as seriously as I can because the goal is to be as much as possible a reference for a very small Haskell compiler that like is structured as close to as possible as to a real one, but it is a toy compiler. The thing we are compiling looks like Rust, with the idea of when I have fixed the last incompatibility, syntax highlighting, formatters, everything that Rust tools will work on this language, even if it's different. And it looks like this more or less. The only thing that is wrong now at the moment is I have this one character here for struct expressions because of an ambiguity in the grammar that I need to fix. But it is like a lot simpler. There's no traits, there's no pointers. Like it is a very, very simplified version of Rust. And the reason it is such a simplified version of Rust is because I am not targeting, the goal is not to generate like an actual binary at the end. The goal is to target an esoteric language, and I want to target a stack-based esoteric language. And more specifically, I want to target the Piètre programming language, which in Piètre, the source code is an image. This is a valid Piètre program that was generated by the backend of the compiler because all of the code, not code generation, the assembly linking part of the compiler already work. This is from two functions that do like print a character and return. They do nothing interesting. This is not an interesting program, but this is a valid Piètre program. And the goal is to translate Rust-like code into this. I have an introduction to the project on YouTube, which you can find the link of it either looking at my site somewhere in those links or on the page of the project, on the GitHub page of the project. There's a link to the YouTube introduction video that talks about like how does this language work and what are we trying to do here. But that's the goal. I have some side goals as well. One of them is a thing I worked on a month ago, was the next stage of the compiler, which is the lowering into IR. So we've finished parsing, validating the thing. We generate an intermediary representation that can be used to then do code generation and stuff. The IR of this project is strongly inspired by the LLVM IR, with the goal of being basically compatible. So what I will want to do is at some point as a side project, do a thing where I convert our IR into the LLVM IR so that I can use the LLVM backend to compile our programs so that we can still try to see what it looks like if we make an actual binary of the program that we have made. But we are not there yet. I'm just going to try for a few more minutes to see if there are some trivial things I can fix in the code at the moment. But since the top level functions are just like not there yet, we are not at the point where I can compile everything this evening. Plus, no, I'm not using a very fancy window manager. I'm just using XFC, which is the one I've used for 2 decades at this point. And it's just, I really like, I have a bunch of virtual desktops, but in each of them, I mostly have full screen windows, basically. At the moment, this is my main non-employment project, basically. I sometimes have more than one in flight. Last year, I was doing a Rust library to provide a Rust binding to the paperless NGX API, which ended up being quite a fun project that I never actually finished. Projects I would like to work on as side projects, I have a list that's too long to fit in the margins of this video. I have so many that I would like to work on. I have a video game project that at some point I'll get back to, but that I've had in my mind for probably a decade at this point that I've never actually worked on. But that's the way of side projects. They accumulate. Okay, so why do I have two functions, name, validate, type, alias, type? This one gets as an argument a function f. Yeah, which game engine to use? I mean, in the past, I I've 3, 4 times started writing my own game engine. And now, if I want to write a game, I'm just going to use Godot and just write it in a Godot script and not bother with writing my own game engine because I've been. It's fun. It's fun to try at least once. It's fun to try at least once. But it was easier to do when I was still on OpenGL 4, and you still have like the direct mode, and you didn't have to worry about shaders or anything like this. Just GL begin, GL end to your heart's content, which was ugly, but easier. There is a Discord dedicated to game programming in Haskell, in which I am, but I'm not active. I don't remember the name, but I'll try to see if I can find the name of it and put it next time. I think it's a public server, if I remember correctly. No, I don't see it quickly, but there is a game programming in Haskell Discord if you want to do that. But again, in my case, I would just like use Godot and just use Godot script and not worry about the engine. I think I say that, but Okay, I just want to figure out why I have two functions called validate type alias type. Validate type alias type. I use this in validating a concrete type. That makes sense. And here I give it as an argument a function, which is go, which is the recursive thing for how to validate. Yes, because I use this with a different argument depending on whether I'm validating a type, a concrete type, a partial type, or a parameterized type. So the validate type alias type will be this one that takes a function as argument. Okay, that makes sense. What is the other one then? It is not called by anything, okay? So this one is probably wrong. Is that the old version before I did this one? It might have been. A speed run for Rayleigh and Haskell. 1 hour, that's fascinating. Thanks for the link. So I think this one is wrong. I think this one is correct. We retrieve the type alias, we validate the parameter count, we create the mapping, and we go recursively. Yeah, I think this one is just outdated. Not in scope. Path info. Okay. Oh yeah, this thing has nothing. Let's go to validation. And let's copy that. And hope that at least one of those is correct. Ah, yes, I want pattern synonyms. And I don't need template Haskell in this thing, so pattern synonyms. I'm starting to try to compile this. I should stop here, I think. Oh, wait, no, I do need template Haskell. Duh. Not in scope name tree. That's because this might end up being a circular import. This might end up being a circular import. Oh wait, no, this is because name I at some point introduced the same kind of complicated. This is no longer the case. Okay, we're good. No instance for show base name. Yeah, that's correct. It's missing. Let's fix that. Oh, do I put it on the same line or do I put it on the line after? I think I'm consistently putting it on the same line. Let's keep that. Yeah, I suppose I can do that as well. Generic and therefore hashable. I definitely index thing by base name, so I want that to be hashable. Not needed. It's great. We like... Okay, and now we are back to common. Enum info is not parameterized by the phase, so this is just a deriving show, and this is no longer required. Yeah, okay. I am gonna stop here because if I start doing this, that's gonna take hours. That's gonna be tomorrow's work, basically. Tomorrow is we put everything we've been working on for a while together to make this thing compile. And tomorrow we get a point where hopefully... Oh, was diagnosis not saved? What was wrong about it? Yeah, okay. So yeah, tomorrow we put everything together and we get back to a point where we can continue working back on the IR and everything else and the simplification phase and all of that. Whew. This refactor has been a lot of work, but I'm glad that we've made progress on this. I'm still on a branch in which nothing compiles. My commit messages are getting absolutely horrible. When we get back to development on dev, I'll make a bit of an effort. Okay. I'll stop here for the evening. I'll do some effort on like putting stuff on YouTube. I'm very late on that, sorry about that. And trying to clip the monad clip from today and the AI clip from today. And put that either on YouTube or try to like keep them on highlights on Twitch or something like this. We'll see how I do that. Anyway, thank you everyone for tuning in. I'll see you all tomorrow.